There is something wrong with the world around you, and the unsettling part is that you cannot see it. You have never been able to see it. You walk through your days touching surfaces, breathing air, watching light bounce off objects, and register in your eyes, and everything feels solid, reliable, continuous. The coffee in your cup cools at a predictable rate. The floor holds your weight without hesitation. The sun rises in the east and sets in the west, and has done so for as long as any human being has ever been alive to watch it. And because all of these things happen with such astonishing consistency, you have built an entire inner narrative around the idea that reality is stable, that it plays by rules, that if you understood those rules well enough, you could predict anything, explain anything, control anything. Scientists have spent centuries reinforcing this narrative. Philosophers have built entire systems of thought on top of it. Civilizations have risen and collapsed and risen again on the foundation of this single quiet assumption that the world is real, that it behaves consistently, and that it can, at least in principle, be fully understood. But something is beginning to crack, not in a dramatic, cinematic way, not with the sound of thunder or the splitting of the earth beneath your feet. It is something far more subtle, far more disturbing, and far more difficult to look at directly. The crack is appearing in the very framework that scientists use to describe reality itself, and the more carefully they look at it, the more they realize they cannot explain it away. You have to understand just how profound that statement is. Science is not a collection of interesting ideas. It is the most rigorous, most tested, most systematically verified method that human beings have ever devised for understanding the world. It does not deal in feelings or intuitions or hunches. It deals in evidence, in repeatability, in falsifiability. When a physicist makes a claim about the nature of the universe, it is because that claim has been tested against reality thousands of times, in different laboratories by different researchers, using different equipment, and the results have always come back the same. That kind of consistency is not something you take lightly, and yet right now in some of the most respected scientific institutions in the world, in the offices and laboratories of some of the most brilliant minds alive, there are conversations happening that no popular science article can quite capture. Conversations that go beyond anomalies, beyond puzzles, beyond the ordinary gaps in knowledge that science has always lived with. These are conversations about whether the picture of reality that science has constructed, the picture that has been so reliable for so long, might be missing something so fundamental, so deep, so structurally important, that fixing it would not mean adding a new chapter to the textbook. It would mean rewriting the entire thing from the beginning. You might be tempted at this point to settle in with the comfortable idea that science always has open questions, that there are always mysteries, and that none of them are quite as alarming as they sound when someone with a dramatic voice describes them on the internet. That is a reasonable instinct. It is the instinct of a rational person who has been burned before by overblown headlines about the end of physics or the breakdown of everything we thought we knew. And it is true that science lives in a state of perpetual incompleteness, that not knowing things is, in a very real sense, the whole point. But there is a difference between the ordinary incompleteness of knowledge, the kind where you simply have not gathered enough data yet, and a deeper, more structural kind of incompleteness, a kind where the very tools you are using to investigate reality seem to be telling you that reality itself does not behave the way it should, where the anomalies are not at the fringes but at the center, where the questions are not about what you have not measured yet, but about whether measurement itself is doing what you thought it was doing. That kind of incompleteness is different. It does not feel like standing at the edge of a field, peering into the dark at things not yet explored. It feels more like standing on a floor that you suddenly suspect is not quite as solid as it looked. To begin to understand what is happening, you need to go back to the world as it appears to you right now, in this moment, in the immediate experience of being a conscious creature in a physical environment. Look around you. Notice how consistent everything is. The walls of the room you are in are not flickering. The objects on your desk or your table are not spontaneously rearranging themselves. You do not wake up each morning to find that the laws of physics have shifted slightly overnight, that gravity pulls sideways now, or that time is flowing in the wrong direction. Everything maintains itself with a kind of profound, almost boring reliability. This is what philosophers call the principle of uniformity, and it is not just a vague feeling. It is the bedrock of scientific reasoning. If the laws of nature changed from place to place or from moment to moment, prediction would be impossible, and science would be impossible along with it. The reason you can perform an experiment in Tokyo and get the same result as in Toronto is because the universe, apparently, plays by the same rules everywhere and at every time. This assumption is so foundational, so deeply woven into the practice of science, that most scientists barely think about it. It is like the air, everywhere, invisible, taken entirely for granted, and the assumption has served humanity extraordinarily well. In the 16th and 17th centuries, a small number of extraordinarily brave thinkers began to apply mathematics to the motion of physical objects. And what they discovered was staggering. The universe was not chaotic or arbitrary. It was geometric. It was mathematical. Galileo looked at falling objects and found that they did not just fall, they fell according to a precise equation, one that worked every single time. Newton looked at the moon hanging in the sky and realized it was doing exactly what a falling apple was doing. Both objects pulled by the same invisible force, governed by the same elegant law. He wrote that law down, and with it he could predict the motions of planets with an accuracy that had seemed impossible just years before. When he used his equations to predict the location of planets centuries into the future, the predictions matched, not approximately, not roughly, exactly. The universe, it turned out, was not mysterious in the way that people had feared. It was not arbitrary, not capricious, not driven by the whims of gods or demons. It was lawful. It was orderly. It was, in principle, completely predictable. This revelation did not just change science, it changed what it meant to be a human being living in the world. If everything operated according to fixed laws, then knowledge was not just comforting, it was power. Power over disease, over distance, over death itself. The scientific revolution was not just an intellectual event, it was an existential turning point. Over the centuries that followed, the picture only got clearer. James Clerk Maxwell unified electricity, magnetism, and light into a single framework of equations so elegant that physicists still describe them with something close to reverence. Darwin showed that the astonishing diversity of life on Earth was not a mystery, but a consequence, something that followed with mathematical inevitability from a few simple principles applied over vast stretches of time. Chemists mapped the building blocks of matter into the periodic table, and that table turned out to have a deep mathematical structure, one that could be derived from first principles once you understood enough about the atom. Mendel counted peas and discovered the mathematics of heredity. Einstein showed that space and time were not fixed containers in which events happened, but dynamic, flexible geometries that bent and curved in response to mass and energy. And his equations were so precise that they predicted phenomena, the bending of starlight around the sun, the existence of gravitational waves, the behavior of GPS satellites in orbit, that would not be observed for decades after he wrote them down. Every single time the universe matched the math, every single time nature obeyed. It was almost as though the universe was conspiring to be understood, as though reality was reaching out to meet the minds that were trying to grasp it, as though some invisible hand had arranged everything so that the laws would be beautiful, that they would be consistent, that they would yield to inquiry. The universe, it seemed, wanted to be known. You were born into this world. Not the literal scientific revolution, of course, but into the worldview it produced, into the cultural and intellectual atmosphere that it generated. Even if you have never taken a physics class, even if you could not write down a single equation, you carry this worldview inside you. You believe, without thinking about it, that the world works by rules, that effects have causes, that things do not simply appear out of nowhere, that if you flip a light switch, the light will come on. Not because of magic, but because of an unbroken chain of causes and effects that you could, in principle, trace all the way back from the photons hitting your retina, to the electrons moving through the wire, to the generator at the power plant, to the turbine spinning in the river or the combustion chamber or the nuclear reactor. Everything connected, everything explicable, everything, in principle, knowable. This is not just a scientific belief, it is a deeply personal one. It is the foundation of your sense of agency in the world. If things happened randomly, if cause and effect were not reliable, then planning would be meaningless, prediction would be impossible, and the entire architecture of human civilization, from medicine to engineering to agriculture to economics, would collapse overnight. The reliability of reality is not just a feature you appreciate, it is the ground you are standing on. And this is precisely what makes what is coming next so unsettling. Because there is a domain of reality that science has been exploring for roughly a century now, a domain that lies beneath the surfaces you touch and the air you breathe and the light you see, a domain of almost incomprehensible smallness and almost incomprehensible strangeness. And in that domain, the rules are different. Not just a little different, not just more complex versions of the familiar rules. They are different in a way that is, even now, after 100 years of study and thousands of experiments and every tool that human ingenuity has been able to bring to bear on the problem, not fully understood. This domain is the quantum world, the world of atoms and electrons and photons and the particles that make up particles, and the theory that describes it, quantum mechanics, is the most precisely verified theory in the history of science. Its predictions have been tested and confirmed to an accuracy of better than 1 part in a trillion. No other scientific theory even comes close. And yet, the physicists who work with it every day, who have spent their careers applying it and refining it and extending it, will tell you something remarkable if you ask them honestly. They do not know what it means. They know how to use it. They know how to apply it. They can calculate with it and predict with it and build technology with it. But the question of what is actually happening, what the equations are actually describing, what reality looks like at the quantum level, when no one is measuring it, that question remains after a century of argument and analysis and philosophical debate, genuinely, profoundly, disturbingly open. Let that settle for a moment, because it is easy to read past it. The most precise and successful scientific theory ever created, the theory that explains the behavior of every atom in your body and every photon of light in this room, the theory on which the entire modern technological civilization runs, from the transistors in your phone to the lasers in your fiber optic cables to the nuclear power plants that some countries use to light their cities. That theory, the most tested piece of human knowledge in existence, describes a reality that no one fully understands. Not because the math is too hard, not because the experiments are too difficult, but because when you look carefully at what the math is actually saying, when you try to translate it into a picture of what is actually happening in the world, the picture you get is deeply, profoundly, almost incoherently strange. Strange in ways that physicists themselves argue about passionately and without resolution. Strange in ways that seem to violate the very foundations of the common-sense reality you have been building your understanding of the world on since the day you were born. The strangeness begins with something called superposition. In the world you experience, objects have definite properties. Your chair is in a specific location. It has a specific color, a specific mass, a specific temperature. It is not in 2 places at once. It does not have 2 different masses simultaneously. It does not exist in a state that is somehow both red and blue at the same time. That kind of dual existence is simply not part of your experience of reality. But at the quantum level, things are different. An electron, for example, does not have a definite position until you measure it. Before measurement, it is described by a wave function, a mathematical object that assigns probabilities to different possible positions. The electron is not hiding in one of those positions, secretly existing there even though you do not know which one. According to the standard interpretation of quantum mechanics, it is genuinely in a superposition of multiple positions, existing in a kind of blurred state, spread out across space in a way that has no analogy in ordinary human experience. This is not a gap in your knowledge. It is not that the electron really does have a definite position, and you just do not know where it is. The mathematics specifically, definitively, unmistakably predicts that the electron has no definite position, that the superposition is real, that the blur is not in your head, but in the world. And this has been tested. The experiments are not ambiguous. The universe actually, genuinely behaves this way at the quantum level. But here is the part that should make you stop. When you measure the electron, when you look for it, when you do something to it that forces an interaction with it in the physical world, something happens. The wave function collapses. The blur becomes a point. The smeared probability distribution resolves into a single definite position. The electron is suddenly here, or there, or somewhere, but it is somewhere specific and it stays that way. The measurement has done something to reality. The act of looking has changed what is there. This is called the measurement problem, and it is not a quaint, philosophical puzzle that physicists chuckle about at conferences and then set aside. It is one of the deepest, most argued about, most genuinely unresolved problems in all of science. What happens during measurement? What causes the wave function to collapse? What is the relationship between the observer and the observed? Does the universe actually have definite properties? Or do those properties only come into existence when something looks? These questions are not answered by quantum mechanics. They are raised by it. And after 100 years and many brilliant minds and no shortage of philosophical ingenuity, they remain unanswered. Not in a way where the answer is close and we just need a little more data. Unanswered in a way that suggests the questions themselves may be pointing at something about reality that our brains are simply not equipped to grasp. The person who first made the measurement problem impossible to ignore was not a philosopher. He was a physicist, and his name was Niels Bohr. Bohr was one of the founding figures of quantum mechanics, a man of extraordinary intellectual depth and unusual personal gravitas, and he had a view of the measurement problem that was practical, almost to the point of being frustrating. His position, known as the Copenhagen interpretation, was essentially this: stop asking what is happening when you are not measuring. The wave function is a tool for predicting measurement outcomes, not a description of some underlying reality. Ask only what you can measure, predict only what experiments can confirm, and do not try to build a picture of the world between observations, because that picture will be meaningless. In other words, shut up and calculate. This is a philosophically radical position, and it is the one that most physicists have defaulted to for most of the past century, not necessarily because they find it convincing, but because it works. It gets the right answers. It passes every test. And so, in the pragmatic culture of working science, it became the default. But here is the problem. If the wave function is not a description of reality, if it is just a tool for calculating probabilities, then what is reality? What is actually happening between measurements? What is the world made of when no one is looking? The Copenhagen interpretation does not answer these questions. It refuses to ask them, and refusing to ask a question is not the same as answering it. The mystery did not go away just because Bohr told his colleagues to stop thinking about it. Other physicists were not so willing to stop thinking. Hugh Everett, a young American physicist working in the 1950s, took the mathematics of quantum mechanics completely seriously and followed it wherever it led. And where it led was terrifying. If you take the Schrödinger equation, the core equation of quantum mechanics, and you apply it not just to small quantum systems, but to everything, including the measuring device, and the physicist, and the room, and the entire universe, then what you get is not a collapsing wave function. What you get is something that never collapses. Instead of one definite outcome emerging from a measurement, what you get is a wave function that branches, that includes all the possible outcomes simultaneously, with the universe splitting at every measurement event into multiple branches, each one containing a different outcome, each one equally real, each one containing a version of you, seeing a different result. This is the many worlds interpretation, and it is not science fiction. It is a serious, mathematically rigorous proposal that has the support of a significant fraction of theoretical physicists. It makes the same predictions as the Copenhagen interpretation, which means it cannot be ruled out by experiment. But the picture of reality it describes is one that is almost impossible to fully absorb. Every quantum event, every interaction between particles, every measurement, every moment of observation, the universe branches. And it has been doing this for 13.5 billion years. The number of branches that would have accumulated by now is so incomprehensibly large that it dwarfs any number you have ever tried to think about. You are, according to this interpretation, one version of you in one branch, in a universe that contains an almost infinite number of other branches, each one containing other versions of you, living different versions of your life. And none of this can be verified. None of it can be tested, but none of it can be ruled out either. And it follows with mathematical necessity from an equation that has passed every experimental test it has ever faced. There is another way the quantum world cracks open the reality you think you live in, and it is called entanglement. Entanglement is, in the words of Erwin Schrödinger, the characteristic trait of quantum mechanics, the feature that separates it most completely. From classical ideas about how the world works, here is what it means. Two particles can interact in such a way that they become entangled, their quantum states linked in a deep and strange way. After they interact, you can separate them by any distance you like. Take one to the other side of the room. Take one to the other side of the country. Take one to the other side of the observable universe. It does not matter. When you measure one of the particles, when you force it to take on a definite value, the other particle instantly, simultaneously, with no time delay, takes on a correlated definite value, not after a signal has had time to travel between them, not after some hidden information has had time to propagate through space. Instantly, this has been tested, not theoretically proposed, not suggested by equations only, but actually tested with actual particles, with actual measurements, in laboratories, with equipment specifically designed to rule out alternative explanations. The correlations are real. They happen faster than any signal could possibly travel. They happen regardless of distance. And they violate a principle that Einstein spent a significant portion of his career defending. The principle that no influence can travel faster than light, that there can be no instantaneous action at a distance, that the universe must be local, meaning that what happens here can only be caused by things that are here, not by things that are somewhere else at the same time. Einstein hated entanglement. He called it spooky action at a distance, and he spent years trying to find a way around it, to show that the apparent non-locality it implied was just an artifact of an incomplete theory, that there were hidden variables underneath quantum mechanics, hidden properties of the particles that determined their behavior in advance, and that the appearance of instantaneous influence was just an illusion, caused by not knowing about those hidden variables. In 1964, a physicist named John Bell showed that this was testable. He derived a mathematical inequality that any theory with hidden variables would have to satisfy. If quantum mechanics was right and hidden variable theories were wrong, the inequality would be violated. The experiments were done. The inequality was violated. Again and again and again, in laboratory after laboratory, with increasing precision and increasingly clever experimental designs, closing one potential loophole after another. The conclusion is clear and uncomfortable. The universe is non-local. Things that are separated by arbitrary distances are connected in ways that have no analog in any classical picture of reality. The universe does not respect the kind of local, independent reality that common sense and 300 years of classical physics had led everyone to assume was how things worked. Something is connecting things across space in a way that no mechanism you can imagine, no signal, no field, no force, no hidden wire in the fabric of space-time can account for. The connection is just there, immediate, real, and inexplicable. And you have to understand that this is not just a weird property of exotic laboratory conditions. This is a feature of the fundamental fabric of everything. Every atom in your body, every particle that makes up every molecule and every cell in your brain and your blood and your bones, all of them interact, all of them become entangled, all of them participate in this web of non-local quantum connections that underlies every piece of matter in the universe. The table you are sitting at, the air you are breathing, the photons registering in your eyes right now, all of it is quantum mechanical at its core. All of it participates in the same strange non-local reality that the laboratory experiments reveal. You do not normally notice this because the quantum effects average out at large scales, because decoherence, the process by which quantum systems interact with their environments and lose their quantum character, happens so quickly in warm, complex systems like the ones you interact with every day that the quantumness is effectively hidden. But it is there, under the hood of everything you see and touch and call real. The universe is doing something that no one fully understands, something that violates the most basic assumptions about how space and causality work, and it has been doing it forever, and it will continue to do it, whether you think about it or not. If the quantum world were the only place where cracks were showing in the picture of reality, you might still be able to contain your unease. You might be able to put quantum mechanics in a box labeled things that are weird at small scales, and go back to your ordinary life with the comfortable understanding that, at the scales that matter to you, at the level of chairs and people and planets, everything is still fine. But the cracks are not just at the small scale. They are also at the largest scale imaginable, at the scale of the entire observable universe in the domain of cosmology, and what is happening there is, in some ways, even more deeply unsettling, because while the quantum anomalies involve things that are strange and counterintuitive, the cosmological anomalies involve things that simply should not be there at all, things that appear in the data, like messages in a language that no one can read yet, like signs that something about the universe is fundamentally different from everything the standard model of cosmology predicts. The standard model of cosmology, sometimes called the lambda CDM model, is one of the great achievements of 20th and 21st century science. It describes the history of the universe from a fraction of a second after the Big Bang all the way to the present day, and it does so with extraordinary precision, using data from the cosmic microwave background, the faint afterglow of radiation left over from when the universe was only about 300,000 years old. Cosmologists have been able to measure the composition of the universe, the rate at which it is expanding, the distribution of matter on large scales, the age of the universe, and dozens of other properties to levels of accuracy that would have seemed impossible just a generation ago. The model works. It is consistent. It agrees with observations across a staggering range of scales and epochs. And yet, even within this triumph, something is wrong. Something specific, something quantitative, something that has been measured with enough precision to be beyond doubt, and that simply does not fit. The problem is called the Hubble tension, and it has been growing over the past decade from an interesting puzzle into something that is beginning to genuinely alarm cosmologists. Here is the issue. The universe is expanding. Edwin Hubble showed this in 1929 by observing that distant galaxies are moving away from us, and that the farther away they are, the faster they are receding. The rate of this expansion is described by a number called the Hubble constant, usually denoted h0, and it represents how fast the universe is expanding, measured in kilometers per second per megaparsec. You can measure this number in two fundamentally different ways. One way is to look at the cosmic microwave background, the ancient relic radiation from the early universe, and use the standard cosmological model to extrapolate forward to calculate what the expansion rate should be today. This gives you a value of approximately 67 kilometers per second per megaparsec. The other way is to use a cosmic distance ladder, building up measurements of distance and recession velocity for nearby and intermediate distance objects like Cepheid variable stars and Type Ia supernovae, standard candles whose intrinsic brightness is known, and directly measure the current expansion rate. This gives you a value of approximately 73 kilometers per second per megaparsec. These two numbers do not agree, and the discrepancy, which sounds small when you write it as numbers, is statistically enormous. It is well above the threshold of what scientists call 5 sigma, meaning the probability that the disagreement is due to random error is less than 1 in 3.5 million. This is not noise. This is not a measurement artifact. The universe, measured two different ways, gives two different answers for how fast it is expanding, and no one knows why. When a discrepancy like the Hubble tension shows up in a field like cosmology, the first instinct is always to look for mistakes. Maybe there is a systematic error in one of the measurements. Maybe some of the assumptions that go into the distance ladder are slightly wrong. Maybe the cosmic microwave background analysis is using an incorrect model. Physicists and cosmologists have spent years looking for these mistakes, scrutinizing the measurements from every angle, checking the analysis, pipelines, looking for hidden assumptions, testing alternative methodologies, and they have found some things, small issues, potential sources of error that might nudge the numbers slightly, but nothing that closes the gap, nothing that makes the two values agree. The more precisely people measure, the clearer the tension becomes. As of the past few years, the consensus among cosmologists is that the Hubble tension is real, that it is not a measurement error, and that it is telling us something. The question is what? And the most serious answers on the table are not small fixes. They are radical restructurings of the entire cosmological model. Some researchers are proposing that the universe went through a phase of early dark energy, a period in its first 100,000 years when an unknown energy field briefly accelerated its expansion before fading away. Others are suggesting that there is new physics in the dark sector, that dark matter or dark energy, or both, behave differently than the standard model assumes. Others are suggesting, more quietly but with increasing urgency, that the cosmological principle itself might be wrong, that the universe might not be as homogeneous and isotropic as the model requires, that there might be large-scale structures, flows, or inhomogeneities that are distorting all of our measurements in ways we have not accounted for. Each of these possibilities is extraordinary. Any one of them would represent a fundamental shift in the way cosmologists understand the universe. And yet, the data keeps demanding one of them. The Hubble tension is not the only cosmological anomaly that is making astronomers uneasy. There is also the matter of dark matter itself, which is worth looking at carefully because the story of dark matter is a perfect illustration of how strange the scientific picture of reality has become. Dark matter is matter that does not interact with light. It does not emit it, does not absorb it, does not reflect it. It is completely invisible to every kind of electromagnetic observation. It passes through ordinary matter with almost no interaction, like a ghost moving through walls. The only way to detect it so far is through its gravitational effects on the things around it, and those effects are undeniable. The rotation curves of galaxies, the way stars orbit around their galactic centers, are completely inconsistent with the amount of visible matter those galaxies contain. If galaxies were held together only by the gravity of their visible stars and gas, they would fly apart. The outer stars are moving too fast. The only way to account for their speeds is to posit a massive, invisible halo of additional matter surrounding every galaxy. A halo that contains several times more mass than all the visible matter in the galaxy combined. This pattern repeats across hundreds of thousands of galaxies. It appears in the way galaxy clusters bend light from objects behind them through gravitational lensing. It appears in the large-scale structure of the universe, the way galaxies cluster together in a cosmic web of filaments and voids. The evidence for dark matter is overwhelming, multiplied, and consistent across completely independent lines of observation. It is not in doubt. Something is there, and it has mass, and it is massive, and it makes up roughly 27% of the total energy content of the universe. But here is the problem. Despite decades of increasingly sensitive and increasingly creative experimental efforts, no one has ever directly detected a dark matter particle. Not a single one. The leading theoretical candidates, the so-called weakly interacting massive particles, or WIMPs, were extremely well motivated theoretically. They arose naturally from extensions of the standard model of particle physics. They had the right mass range and the right interaction cross-section to explain the observed dark matter abundance. They were, in the words of many physicists, almost too good to be true. And they were, in the end, too good to be true. Multiple, enormous, extraordinarily sensitive underground detectors, tanks of liquid xenon surrounded by layers of shielding buried deep underground to block cosmic ray interference, searched for WIMPs for decades and found nothing. Not a signal, not a hint, not an ambiguous blip that might have been real, just silence. Other experiments looked for dark matter in particle accelerators, in space-based detectors, in pulsar timing arrays, in axion detectors, in every way anyone could think of, and the silence continued. Dark matter accounts for more than a quarter of everything in the universe, and it has never once revealed itself in any experiment specifically designed to find it. At some point, the silence stops being just a null result and starts being a message. Maybe the dark matter particles are simply very weakly interacting, more weakly than any of the models predicted. Maybe there is no dark matter particle at all, and the gravitational effects are produced by some modification of gravity that is not yet understood. Maybe there is something about the relationship between matter, gravity, and space that no current theory has captured. The silence of the dark matter experiments is not telling you that dark matter does not exist, but it is telling you that if it does exist, it is nothing like anything in any current theory, which means that a quarter of the universe is made of something that is nothing like anything you know how to think about. And then there is dark energy, which is even more mysterious than dark matter, and the source of perhaps the most profound cosmological puzzle in existence. In 1998, two independent teams of astronomers were using Type Ia supernovae, those stellar explosions whose luminosity is well calibrated enough to use as cosmic distance markers to measure the deceleration of the universe's expansion. The assumption was that the expansion was decelerating, slowing down under the gravitational attraction of all the matter in the universe. This seemed obviously correct. Gravity is attractive. Matter curves space-time inward. The expansion should be slowing down. But when the data came in, it said the opposite. The universe was not slowing down. It was speeding up. The expansion of the universe was accelerating. Distant galaxies were being pushed apart faster and faster over time, not pulled back together, not decelerating toward a future big crunch, but accelerating away from each other, driven by some form of energy embedded in the fabric of space-time itself. This discovery won the Nobel Prize in 2011, and it is entirely real and entirely verified. But the thing that is driving it, the dark energy, is one of the greatest mysteries in all of physics. The standard model of cosmology treats dark energy as a cosmological constant, a uniform energy density that permeates all of space, described by a single number. Einstein actually introduced this term in his equations of general relativity, then famously removed it, calling it his greatest blunder. When Hubble showed that the universe was expanding, then it was put back in when the expansion was found to be accelerating. The cosmological constant fits the data beautifully, but when theorists try to calculate its value from first principles, using quantum field theory, which should describe the quantum fluctuations of empty space that contribute to this energy density, they get a number. And that number is wrong by a factor of somewhere between 10 to the 60th and 10 to the 120th. This is the largest discrepancy between theory and observation in the history of science, by an enormous margin. It is not just a slightly wrong prediction. It is a prediction that is off by a factor that is larger than the number of atoms in the observable universe. A factor so outrageously, embarrassingly, catastrophically wrong that it represents, in the words of some physicists, the worst prediction in the history of physics. And this is not a peripheral issue. This is not a small corner of physics where the theory is a little rough around the edges. Quantum field theory is the framework that underlies all of particle physics. The standard model of particle physics, which describes all known particles and forces except gravity, is a quantum field theory, and it is one of the most precisely verified theories in science. It successfully predicted the existence of the Higgs boson, confirmed in 2012, and the value of the electron's magnetic moment to an accuracy of 12 decimal places. It is, in one sense, an extraordinary triumph. But when you try to use this same framework to calculate the energy density of empty space, to understand why the vacuum of the universe has the energy density it has, the theory gives a catastrophically wrong answer. Something is deeply inconsistent in the theoretical framework at a level that no one has been able to fix. There are proposed solutions, adjustment mechanisms, ways of canceling the enormous contributions to vacuum energy through various theoretical mechanisms, but none of them are fully satisfying. None of them emerge naturally from the theory itself, and none of them explain why the actual value of the cosmological constant is not just small but small in exactly the right way to allow galaxies and stars and planets and life to exist. If the cosmological constant were slightly larger, the universe would have expanded so quickly after the Big Bang that matter would never have had time to clump together into galaxies. If it were slightly negative, the universe would have collapsed long before any stars could form. The value it has is, in some sense, that is difficult to fully articulate without sounding like you are saying something profoundly strange, almost exactly right for the existence of things like you, and no one has a convincing physical explanation for why. This is a good moment to pause and take stock of what you have encountered so far, not as a resolution, not as a summary, but as a way of feeling the weight of what has been assembled. In the quantum realm, the fundamental constituents of reality do not have definite properties until they are measured, and the act of measurement causes something to happen that is not explained by the theory. Particles that are arbitrarily far apart are somehow connected in ways that violate locality. The most successful theory in the history of science describes a reality that its own practitioners cannot agree on how to interpret after 100 years of trying. In the cosmological realm, the universe is expanding at a rate that two independent measurement methods disagree about in a statistically overwhelming way. A quarter of the universe is made of something invisible that has never been directly detected. The energy density of empty space is incomprehensibly small by theoretical prediction standards, but has never been explained. And the value of that energy density is precisely tuned to a degree that strains every notion of coincidence you have ever entertained. These are not separate, disconnected puzzles sitting quietly in their respective corners of science. They are cracks running through the same foundation, appearing in different places but suggesting the same underlying fracture. And the fracture is not in any particular Theory, it is in the picture of reality itself. There is something else happening in physics right now that does not get discussed as openly as the Hubble tension or dark matter, something that lives more in the conversations between physicists after conference talks than in the headlines of science journals. But that has been growing in intensity and urgency for decades. It is a crisis of unification, one of the deepest aspirations of theoretical physics, running like a thread through the entire history of the field has been the dream of a single unified description of all of nature. A master theory that would encompass all forces, all particles, all phenomena, from the smallest quantum fluctuation to the largest cosmological structure, in a single coherent mathematical framework. This dream has driven some of the greatest achievements in physics. Maxwell unified electricity and magnetism. Einstein unified space and time, and then unified gravity with the geometry of space-time. The Standard Model unified the electromagnetic force with the weak nuclear force, and then incorporated the strong nuclear force into a single quantum field theory framework. Each step of unification revealed a deeper level of order, a higher level of coherence, a more elegant structure underlying the apparent diversity of nature. Each step made it seem like the final theory, the ultimate unification, was not just possible but close. And then, things stopped working. The problem is gravity. Gravity, the oldest known force, the one that Newton described and Einstein perfected, the force that shapes the large-scale structure of the universe and holds you to the surface of the Earth, is the one force that refuses to fit into the quantum mechanical framework. The Standard Model of particle physics describes three of the four known forces, electromagnetism and the strong and weak nuclear forces, using quantum field theory, and it works with extraordinary precision. But every attempt to incorporate gravity into this framework, to create a quantum theory of gravity, runs into catastrophic mathematical problems. The calculations produce infinities, not large numbers, actual infinities, meaningless divergent quantities that tell you the calculation has gone wrong somewhere in a fundamental way. Physicists have a bag of tricks called renormalization for dealing with infinities in quantum field theory, and it works beautifully for the other forces. But for gravity, renormalization fails. The infinities cannot be removed. The theory is not renormalizable, which in the language of physics means it is mathematically incomplete, that it breaks down at short distances and high energies, that it cannot be the final word. And this is not a minor technical issue. This is a fundamental incompatibility between the two most successful and most fundamental theories in all of physics. Quantum mechanics and general relativity both work extraordinarily well in their respective domains, but they cannot both be right in the same domain at the same time. They are mathematically inconsistent. They describe reality in ways that contradict each other. And since everything in the universe is both subject to gravity and subject to quantum mechanics, this means that the theoretical framework you are using to describe the universe is, at some level, incoherent. You have two descriptions that each work perfectly in their domain, but that cannot be combined, that cannot be merged, that resist every attempt at unification. It is as if you had two maps of the same territory, both internally consistent and accurate for their respective regions, but that showed the territory to have a completely different shape when you tried to lay them side by side. String theory was supposed to solve this. For several decades, beginning in the 1980s, string theory was the dominant framework for attempting to unify quantum mechanics and gravity, and the excitement around it was enormous. The central idea is that the fundamental constituents of nature are not point particles, but tiny, one-dimensional vibrating strings of energy, and that the different particles in nature, electrons, quarks, photons, gravitons, are just different vibrational modes of these strings. The way a violin string playing different notes produces different sounds. String theory automatically incorporates gravity, resolving the mathematical incompatibility that plagues other approaches. It requires extra dimensions of space beyond the three that you experience, dimensions that are curled up so small that they are invisible at any energy scale accessible to current experiments. It has deep connections to other areas of mathematics and produces structures of extraordinary elegance and richness. At its peak, it attracted some of the most talented physicists and mathematicians of the late 20th century, and the hope was that it would converge on a unique, beautiful, final theory of everything. But something went wrong. As researchers explored string theory more deeply, instead of converging on a unique theory, they kept finding more versions of it. different ways to curl up the extra dimensions, different configurations, different vacua, each one corresponding to a different possible universe with different physical constants. The number of these configurations grew, then it grew more. Then it became clear that the number of distinct string theory vacua was not 10 or 100 or a million. The current estimate is something on the order of 10 to the 500, an almost incomprehensibly large number of possible universes, each with different laws of physics, each theoretically equally valid, none obviously preferred over the others. This is called the string theory landscape, and it has a deeply troubling implication. If string theory is correct, and there are 10 to the 500 possible versions of the universe, then it cannot predict which one we live in. It cannot tell you why the constants of nature have the values they have. It cannot explain why the cosmological constant is the tiny number it is, or why the electron has the mass it has, or why there are exactly 3 generations of particles in the Standard Model. All of these things become, in the landscape picture, accidents of which vacuum our particular universe happened to land in, not explained, not derived, just selected, presumably by some process that generated an enormous number of universes, from which we selected ours by the simple fact of being here to observe it. The anthropic principle, the idea that we observe the universe we do, because it is the only kind of universe in which observers like us can exist, has been around for a long time and has always been controversial. But in the context of the string landscape, it has taken on a new and more troubling character. If the landscape is real, if there really are an astronomically large number of possible universes with different physical constants, and if we necessarily find ourselves in one of the subset that permits our existence, then the apparent fine-tuning of the constants of nature is no longer a mystery to be explained. It is just a selection effect. We observe what we observe because observers only exist in universes like ours. This reasoning is not obviously wrong. It might even be correct. But it has a devastating consequence for theoretical physics. If you can explain any observed value of any physical constant by invoking the landscape and the anthropic principle, then the theory has effectively lost its predictive power. You can no longer derive the constants. You can no longer explain them. You can only note that they are what they must be for us to exist. This is, in the words of some physicists, not physics. It is the abandonment of physics and string theory, the framework that was supposed to be the triumphant final unification of all of nature, may have delivered not a theory of everything but a framework that can accommodate anything, which in science means it is in danger of explaining nothing. The response to this situation among theoretical physicists has been varied and emotionally charged in a way that is unusual for a field that prides itself on rational dispassion. Some physicists remain committed to string theory and believe that the landscape problem will eventually be resolved, that some principle will be found that selects a unique vacuum and restores predictive power. Others have become deeply skeptical, arguing that a theory with no unique predictions is not a scientific theory at all, regardless of its mathematical beauty. Lee Smolin, in his book The Trouble with Physics, and Peter Woit, in Not Even Wrong, made this argument publicly and forcefully, and the response from string theorists was sharp and sometimes acrimonious. But beneath the professional disagreements and the institutional politics, something important was being said. Physics had reached a point where its leading candidate for the fundamental theory of everything was not making falsifiable predictions. The theory was not wrong, in the usual sense. It was, in a specific and troubling way, not even testable. And if a theory cannot be tested, if there is no experiment that could in principle distinguish it from an alternative, then it has crossed a line that separates science from philosophy, or mathematics, or perhaps from a story that makes us feel better about not knowing the answer. Meanwhile, a completely different approach to quantum gravity had been developing in parallel, one that took the insights of general relativity more seriously and tried to quantize not matter fields on a fixed space-time background but space-time itself. This approach, broadly called loop quantum gravity, suggests that space is not a smooth, continuous fabric, but is instead made up of discrete quantized units, a granular structure at the smallest scale, the Planck scale, roughly 10 to the minus 35 meters, where quantum effects of gravity become important. In this picture, space itself is a kind of network, a spin foam, a graph of nodes and edges with no continuous background, and the ordinary space that you experience is an emergent, macroscopic approximation of this fundamentally discrete and quantum structure. Loop quantum gravity makes some interesting and falsifiable predictions, particularly about the propagation of high energy photons, which should travel very slightly slower than low-energy photons if spacetime has a granular structure, a tiny but in principle measurable effect. Observations of gamma-ray bursts from distant galaxies have looked for this effect and have not yet found it, which places constraints on the theory but does not rule it out conclusively. What loop quantum gravity has not yet succeeded in doing is recovering the known physics of particles and forces, the Standard Model, from within its framework. It describes quantum spacetime but does not yet describe the matter that lives in that spacetime. So you have, on one side, string theory, which describes matter and forces beautifully but cannot make unique predictions, and on the other side, loop quantum gravity, which describes quantum spacetime beautifully but cannot yet incorporate the physics of matter. Neither is complete. Neither has succeeded. The unification that physics has been striving toward for a century remains as elusive as ever. You might wonder at this point whether the problem is simply that physics needs more time, that the questions are hard, the mathematics is formidable, the experiments are expensive, and that given enough time and enough talent and enough resources, the answers will come. History gives some support to this view. Newton's mechanics were incomplete for over 200 years before Einstein replaced them with something deeper, the inconsistencies in classical electrodynamics that eventually led to quantum mechanics festered for decades before they were resolved. Maybe the incompatibilities between quantum mechanics and general relativity are just another in a long series of puzzles that will eventually yield to sustained inquiry, that the next generation of physicists will find the key, build the right mathematical framework, perform the right experiment, and the picture will click into place with the satisfying clarity of every previous revolution. But there is a reason to think that this time is different, and it is not just a feeling, it is something more structural. In previous revolutions in physics, the anomalies that drove them were specific, quantitative, and directly tied to experimental observation. The ultraviolet catastrophe, the failure of classical physics to describe the spectrum of radiation from hot objects, pointed directly toward quantization. The failure of the Michelson-Morley experiment to detect the ether pointed directly toward special relativity. In each case, there was a clear, measurable discrepancy between theory and experiment, and the resolution, when it came, was a new theory that not only fixed the discrepancy, but unified a wider range of phenomena. What is different now is that the most fundamental problems in physics are not primarily about disagreements between theory and experiment. They are about disagreements between theories, about the internal incoherence of the framework, about questions that experiments cannot currently answer and might never be able to answer. The Hubble tension and the dark matter problem are genuine empirical puzzles, but the deeper issues, the measurement problem in quantum mechanics, the incompatibility of quantum mechanics and general relativity, the fine-tuning of the cosmological constant, these are not things that a new experiment is going to resolve in the next few years. They point at something more fundamental. They point at the limits of the framework itself. And if you follow that thread, if you pull on the idea that the framework itself might be inadequate, you end up in a place that is genuinely vertiginous, because the framework is not just a collection of equations. It is a set of assumptions about what reality is and how it can be known. It is built on concepts like space, time, causality, locality, and the separability of observer from observed. These concepts feel so basic, so obviously correct, so deeply woven into the fabric of everything you know that it is almost impossible to question them without feeling like you are losing your footing on reality itself. But that is exactly what some of the most serious and careful thinkers in physics are beginning to do. They are beginning to suggest that the deepest problems in physics cannot be solved by adding new particles or new fields or new dimensions within the existing framework. They require questioning the framework itself. They require asking whether space and time, the arena in which all of physics takes place, are fundamental, or whether they are emergent, whether they are properties that arise from something deeper and more fundamental that has no analog in ordinary human experience. They require asking whether causality, the iron chain of cause and effect that underlies every scientific explanation, is a fundamental feature of nature or a useful approximation that breaks down in certain regimes. They require asking whether the sharp boundary between observer and observed between the measurement apparatus and the system being measured is real or artificial, whether it is written into the nature of things or imposed by the limitations of human perception. The idea that space and time might not be fundamental is not new, but it has gained significant momentum in recent years, driven partly by developments in string theory and partly by work in quantum gravity and quantum information. One of the most striking ideas to emerge from this direction is something called the holographic principle, which arose from the study of black holes and has since taken on a life of its own as one of the most provocative proposals in modern physics. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that region, on its two-dimensional surface, like a three-dimensional hologram that can be reconstructed from a two-dimensional image. In other words, the three dimensions of space that you experience might not all be equally fundamental. The physics of the interior of a region might be completely equivalent to, completely describable by, a different theory living on the boundary of that region, a theory with one fewer dimension. This is not just a mathematical curiosity. It has been made precise in the context of string theory through a correspondence called ADS-CFT, discovered by Juan Maldacena in 1997, which establishes an exact mathematical equivalence between a specific theory of gravity and a specific type of curved spacetime and a quantum field theory, with no gravity living on the boundary of that spacetime. This correspondence has been enormously productive as a mathematical tool, providing insights into quantum gravity, black holes, condensed matter physics, and quantum information. But its implications are disturbing in a way that goes beyond its technical usefulness. If it is correct, if gravity in the interior is equivalent to a non-gravitational theory on the boundary, then one of these descriptions is more fundamental than the other, or perhaps neither is fundamental and both emerge from something even deeper. The three-dimensional space in which gravity lives might be, in a precise mathematical sense, not fundamental. It might be a derived quantity, an emergent structure, something that does not exist at the most basic level of reality. The physicist Sean Carroll has written about how the emergence of space and time from something more fundamental would represent a revolution in physics greater than any that has come before, because all previous revolutions, from Newtonian mechanics to general relativity to quantum mechanics, have taken place within the assumption that space and time are the arena. Even quantum mechanics, as strange as it is formulated in terms of particles or fields that exist in space and evolve in time. If space and time are not fundamental, if they are emergent, then the entire language in which physics is written might need to change, and there is no guarantee that the concepts needed to replace it are ones that human minds can grasp intuitively. We evolved to navigate a world of medium-sized objects moving at slow speeds in 3 dimensions of space and 1 dimension of time. The neural architecture that allows you to visualize a room, to plan a path through it, to anticipate the trajectory of a thrown object, was built by evolution to solve very specific problems in a very specific kind of environment. There is no reason to think that this architecture is capable of generating an intuitive understanding of what reality looks like at the Planck scale, or outside space-time, or in a regime where the concepts of space and time simply do not apply. The history of physics suggests that every deeper level of reality requires new mathematical concepts that have no intuitive analog. Complex numbers, Hilbert spaces, fiber bundles, spin-ors, these are not things that anyone has any intuitive feel for. They are abstractions built by the mathematical mind to capture structures that the physical mind cannot directly perceive. And the deeper you go, the more abstract the mathematics becomes, and the more it loses any connection to the world of ordinary sensory experience. This brings you to a possibility that is perhaps the most unsettling of all the things that have been raised so far, a possibility that is not often stated plainly, but that hangs over all of these discussions, like a low cloud. The possibility that the final theory of nature, if there is one, if the universe has a final theory, might be humanly incomprehensible, not just difficult, not just requiring years of study and enormous mathematical training. Incomprehensible in a deeper sense, in the sense that the concepts it requires might not be buildable by human minds at all, that the categories of thought that human evolution has endowed you with might be simply inadequate for grasping the deepest level of what is real. You can think of it this way. A dog has a brain of extraordinary capability compared to most animals. It can recognize individuals, navigate complex environments, understand cause and effect, model the behavior of other dogs and of humans to a significant degree. But a dog cannot understand calculus, not because it has not been taught, because the cognitive architecture that calculus requires, the ability to reason formally about limits and infinitesimals and continuous change, is simply not present in the dog's brain. Now ask yourself, is there any reason to believe that human cognitive architecture is sufficient to understand the deepest level of reality? That evolution, which built your brain to hunt and gather and navigate social hierarchies on an African savanna 100,000 years ago, happened to produce a mind that can understand the ultimate structure of the universe? That seems like an extraordinary coincidence, and yet it is an assumption that lies quietly beneath virtually all of science. The assumption that the universe is not just mathematically describable, but mathematically describable in ways that human minds can, at least in principle, grasp. The philosopher Colin McGinn has written extensively about what he calls cognitive closure, the idea that just as a rat is cognitively closed with respect to the concepts needed to understand Newtonian mechanics, human minds might be cognitively closed with respect to certain problems. Not because those problems are insoluble, but because solving them requires concepts that fall outside the space of concepts that human cognitive architecture can generate. McGinn applies this specifically to the mind-body problem, to the question of how physical processes in the brain give rise to subjective conscious experience, and argues that the reason this problem seems so intractable is not that there is no solution, but that the solution requires a form of thought that human brains cannot produce. The same argument could be made about the deepest problems in physics, the measurement problem in quantum mechanics, the nature of space-time at the Planck scale, the origin of the universe, the explanation for the fine-tuned constants of nature. These might not be problems that human minds cannot solve because they lack data. They might be problems that human minds cannot solve because they lack the cognitive architecture to generate the concepts needed. The equations might be there, already written down in some branch of mathematics that exists but has not yet been connected to physics. But even if someone finds them, even if the math works perfectly, the deeper question of what it means, of what the equations are describing, of what reality looks like at that level, might be permanently beyond human understanding, not because the universe is hiding anything, but because understanding requires a kind of fit between the structure of the mind and the structure of what is being understood, and there is no guarantee that fit exists at every level. You might have noticed that as you have moved through these ideas, the questions have been getting progressively more personal, more internal, moving from the behavior of particles and the expansion of the universe toward the nature of observation itself, toward the role of the mind in constituting reality, toward the limits of cognition. This is not accidental. It is the direction in which the problems actually point. The measurement problem in quantum mechanics is not just about what electrons do. It is about what observation is, about what it means for something to be real, about the relationship between the physical world and the minds that try to know it. And once you start pulling on that thread, the boundary between the physics of the universe and the philosophy of the mind begins to dissolve in a way that is deeply uncomfortable and deeply important. Because the question of whether reality is stable and coherent and fully knowable is not just a question about particles and fields and expansion rates. It is a question about what you are, about how your mind constructs the picture of reality you live inside, and whether that picture is a reliable window onto something real, or a story that your brain tells you to make the chaos of raw sensation navigable. The science of perception has made remarkable progress over the past few decades, and what it has revealed is genuinely startling for anyone who assumed that seeing was simply a matter of light entering the eye and the brain, faithfully reporting what is there. The process of visual perception, which feels to you like an immediate and transparent window onto the external world, is in fact an act of reconstruction. Your brain does not passively receive visual information. It actively constructs a model of the external world, using the incoming sensory data as raw material, but filling in vast amounts of information from prior experience, expectation, context, and inference. The resolution of your visual field is not uniform. Only the tiny central region called the fovea has high resolution. The rest of your visual field is coarser, less detailed, more uncertain. But you do not perceive your visual field as having this graduated quality. You experience it as uniformly sharp, uniformly detailed, uniformly present. Your brain is filling in what is not there, constructing a seamless experience of a fully detailed world from what is actually a patchwork of high-resolution and low-resolution data, stitched together so seamlessly that the seams are invisible. You do not notice the blind spot in each eye, the place where the optic nerve attaches to the retina, and there are no photoreceptors, no ability to see. Because your brain fills it in with surrounding context, you experience continuity between blinks, even though your eyes are periodically shutting off, and the visual input is interrupted dozens of times per minute. The world you see is not the world that is there. It is a world that your brain has constructed from the world that is there, using the world that is there as a guide but never being a simple copy of it. This would be merely interesting if it were confined to the quirks of visual processing, but it goes deeper, much deeper. The experience of a continuous, stable, three-dimensional world persisting through time is not given to you. It is constructed by your brain, moment by moment, from an extraordinary barrage of sensory inputs, motor signals, memories, predictions, and inferences. The philosopher and neuroscientist Anil Seth has argued that consciousness itself is a controlled hallucination, that the experience of being a self in a world is the brain's best guess about the causes of the sensory signals it receives, a predictive model running continuously in the dark interior of the skull, calibrated and updated by sensory feedback but never directly in contact with the external world. If Seth is right, and there is substantial empirical support for this view, then what you call reality, the world as you experience it, is not the world as it is. It is the world as your brain predicts it to be, filtered through the particular architecture of human perception, shaped by evolutionary pressures that had nothing to do with truth and everything to do with survival, calibrated to a particular range of scales and speeds and energy levels that are relevant to the survival of a medium-sized primate on a terrestrial planet. The quantum world is hidden from you, not only because the math is hard, but because your brain was never given the tools to perceive it directly. The large-scale structure of the cosmos is hidden from you not only because the distances are vast, but because your brain evolved on a time scale of years and a spatial scale of miles, and nothing in its architecture prepares it for the reality of billion light-year filaments of matter and the deep time of stellar evolution. You are not perceiving reality. You are perceiving your brain's model of reality, and the question of how well that model corresponds to the underlying thing, the actual reality beneath the model, is one that cannot be answered from inside the model. This is where the simulation hypothesis enters, not as science fiction, but as a genuine philosophical and scientific argument that has been taken seriously by some very careful thinkers. The argument, most famously, formulated by philosopher Nick Bostrom, goes roughly like this. Assume that civilizations can, as they develop technologically, eventually create computational simulations of reality, sophisticated enough to contain conscious beings who believe they are living in a real universe. If this is possible, and there is no obvious reason to think it is not possible in principle, then the number of simulated conscious beings that could eventually exist would vastly outnumber the number of non-simulated beings. If there are 1 trillion simulated universes for every real one, and each simulated universe contains the same number of conscious beings as the real one, then any given conscious being, any one of the minds trying to figure out where they are, is vastly more likely to be in a simulation than to be in the original real universe. This argument is not a proof that we live in a simulation. It is an argument that the prior probability of living in a simulation is not negligible and might even be high unless you are willing to commit to one of two other propositions. Either almost no civilizations ever reach the technological capability to run such simulations, or almost every civilization that reaches that capability chooses not to run them. Both of these escape routes require assumptions about the future of civilization and the ethics of simulation that are themselves far from obvious. So the argument leaves you with a genuinely uncomfortable possibility, not as a thought experiment, but as a real, live, unresolved question. Is the universe you experience the original fundamental reality, or is it a computation running on some substrate in a different, more fundamental reality? The simulation hypothesis is often dismissed as too speculative to take seriously, and there are legitimate reasons to be cautious about it. But what is notable, and somewhat disturbing, is that it is not easy to rule out. You cannot look for the seams of a simulation from inside the Simulation. Any more than a character in a video game could look at the edges of its own computational substrate from within the game world. Any apparent evidence against the simulation, any observation that seems to confirm the reality of the physical world, could in principle be part of the simulation. More interestingly, some physicists have noted that certain features of the universe that seem puzzling or arbitrary from a purely physical standpoint would make perfect sense if the universe were a computational structure. The quantization of space and time at the Planck scale, the discreteness of quantum states, the fact that information seems to be a fundamental quantity in modern physics, the holographic principle, all of these could be interpreted as features of a computational architecture, rather than mysterious properties of a sui generis physical reality. None of this proves the simulation hypothesis, but it illustrates something important. The hypothesis is not simply absurd. It is genuinely hard to rule out, and a hypothesis about the fundamental nature of reality that cannot be ruled out, even in principle, should occupy a more central place in our thinking about what reality is than the reflexive dismissal it usually receives. There is a related idea that does not require any commitment to the simulation hypothesis, but that points in the same disturbing direction, and it comes from the foundations of mathematics. In 1931, Kurt Gödel proved his incompleteness theorems, and these theorems established something about formal logical systems that continues to reverberate through philosophy, mathematics, and theoretical physics. Gödel showed that any consistent formal system powerful enough to describe the arithmetic of the natural numbers contains statements that are true, but unprovable within that system. There are truths about mathematics that mathematics itself cannot demonstrate. This is not a gap in current knowledge, not something that more clever mathematicians will eventually fill in. It is a structural property of formal systems, a permanent, irreducible incompleteness that no amount of effort or ingenuity can overcome. The theorems shattered the dream of Hilbert and others to build mathematics on an absolutely complete and certain foundation. They showed that mathematical truth is not the same as provability, that there is more truth than any formal system can capture, that the territory always exceeds the map. Now, if physics is mathematics, if the universe is, as some physicists believe, a mathematical structure at its core, then Gödel's theorems might apply to it directly. There might be facts about the universe that cannot be derived from any finite set of axioms, truths about reality that cannot be proven from within any physical theory, including the final theory, if there is one. The universe might be, in a rigorous mathematical sense, incompletable, not merely unknown but unknowable, in a way that goes beyond the limitations of instruments or theories and touches the fundamental structure of what can be known at all. Max Tegmark, a cosmologist at MIT, has developed this line of thinking into one of the most radical and in some ways most compelling ideas in contemporary physics. His mathematical universe hypothesis proposes that the universe is not just described by mathematics, but is mathematics, that physical reality is identical to a mathematical structure, that every consistent mathematical structure exists as a physical universe, and that ours is one of them, the one we find ourselves in for the same anthropic reasons that we find ourselves in a universe where the constants permit our existence. This idea, if correct, dissolves the mystery of why mathematics is so unreasonably effective at describing the physical world, the puzzle that physicist Eugene Wigner famously raised in 1960. The answer, on Tegmark's view, is that mathematics is not effective at describing the physical world. Mathematics is the physical world. There is no additional non-mathematical physical stuff. There is just mathematical structure existing in a kind of eternal abstract realm, and we are patterns within one of those structures, mathematical entities who have become complex enough to model the structure they inhabit. If Tegmark is right, then the question of why the universe exists at all, what put the fire into the equations, as Stephen Hawking put it, has a clean answer. The equations do not need fire. Mathematical structures do not need to be instantiated by something physical. They exist in their own right, necessarily, by virtue of their mathematical consistency. And this means that every consistent mathematical structure exists, which means that every possible universe that can be described without contradiction exists, which means that the number of existing things is vastly, incomprehensibly larger than anything you have been imagining until this moment. But you do not have to go as far as Tegmark's mathematical universe to feel the ground shifting beneath your feet. You only have to look carefully at what quantum mechanics already says about the relationship between mathematics and reality, and specifically at a fact that has been sitting in plain sight since the 1920s and has never been satisfactorily explained. When you write down the wave function of a quantum system, you are writing down a mathematical object, a complex valued function, on a configuration space that has no direct analog in ordinary physical experience. When the system consists of two particles, the wave function is defined not in ordinary three-dimensional space, but in a six-dimensional configuration space. For three particles, it is nine-dimensional. For a system of n particles, the wave function lives in a 3n dimensional space. For a system like the brain, or a living cell, or any macroscopic object, the configuration space has an astronomically large number of dimensions, far more than the three spatial dimensions of ordinary experience. And yet this astronomical dimensional mathematical object, living in a vast abstract space, somehow corresponds to the three-dimensional world you experience. How? Why? What is the relationship between the wave function in its enormous abstract configuration space and the ordinary world of tables and chairs and sunsets? Quantum mechanics does not answer this question. It uses the wave function, it predicts with it, it extracts observable quantities from it, but the deeper question of what the wave function is, of what it means for a mathematical object defined in an abstract space to be related to physical reality, remains unanswered. The mathematics works, the correspondence is exact, but the explanation for why the mathematics works is not there. The universe is behaving as though it is a mathematical object, but no one has been able to say what that means in a way that fully satisfies. There is one more domain of scientific inquiry that bears directly on the question of whether something is fundamentally wrong with the picture of reality, and it is perhaps the most intimate domain of all, because it is not about particles or galaxies or abstract mathematics. It is about you, about the fact that you are conscious, that there is something it is like to be you, that the universe you have been contemplating throughout this conversation is being contemplated by a mind, and that the existence of that mind is one of the most profound and least understood facts in all of science. The hard problem of consciousness, as philosopher David Chalmers named it in 1995, is the problem of explaining why physical processes in the brain give rise to subjective experience, why there is something it is like to see red, to feel pain, to hear music, why the electrochemical activity in your neurons does not proceed in darkness without any accompanying inner experience, the way the computations of a thermostat do, but instead generates this extraordinary inner light, this first-person perspective, this felt quality of existence. This is not the same as explaining how the brain processes information, how it integrates sensory signals, how it generates behavior, how it models the external world. All of that can in principle be explained in purely physical terms, and neuroscience has made extraordinary progress on all of it. The hard problem is different. It is the question of why any of that processing is accompanied by experience at all, why there is a subjective inside to the objective outside. Chalmers argued that the hard problem cannot be solved within the existing framework of physical science, because physical science deals with structure and function, with the relationships between things and the behaviors they exhibit, and consciousness is something over and above structure and function. You could, in principle, have a brain that processes information in exactly the same way as yours, performs all the same functions, generates all the same behaviors but has no inner experience, no felt quality, no light on inside. Such a creature is called a philosophical zombie, and while its existence is not physically possible given current understanding, the point is that the concept is coherent, that there is no logical contradiction in the idea of a functional being without experience, and this means that function alone does not explain experience. Something more is needed, and that something more is not in any current physical theory. Consciousness is the one fact about the universe that is absolutely certain, more certain than any other fact, because your experience of it is the only thing you are directly acquainted with, the only thing that does not require inference or instrument. You can doubt the external world, you can doubt the reliability of your senses, you can doubt the mathematics of physics, but you cannot doubt that there is experience happening. Whatever else is uncertain, the fact of your own consciousness is not. And yet, this most certain of facts is the one that physics has the least to say about. It is not in the standard model. It is not in general relativity. It is not in string theory or loop quantum gravity or any other approach to fundamental physics. Consciousness is, in the physics literature, essentially absent, and this absence is not trivial. It might be a fatal flaw, because here is a thought that is difficult to dismiss once it has occurred to you. The entire edifice of science, all the theories, all the equations, all the measurements, all the observations, all the data, is built on and from conscious experience. Every experiment ever performed was performed by a conscious observer. Every measurement was read by a conscious mind. Every equation was written by a conscious hand guided by a conscious brain. Every theoretical framework was constructed by conscious thought. The data that confirms the standard model was interpreted by conscious physicists. The photographs of the cosmic microwave background were analyzed by conscious cosmologists. The gravitational wave signals from colliding black holes were identified by conscious engineers and scientists working at conscious institutions. There is not a single piece of scientific knowledge in existence that did not pass through the filter of conscious experience on its way from the universe to the theory, and yet the theories themselves contain no consciousness. They describe a world of particles and fields and space-time curvature and quantum states, and in none of that description is there any room for the very thing that produced the description. Science has built a picture of reality from which the painter has been entirely erased. And the question of whether a picture of reality that contains no account of the thing doing the picturing can possibly be complete is not a rhetorical question. It is a genuine and deeply serious one. Some physicists and philosophers have responded to this by arguing that consciousness will eventually be explained within the existing physical framework, that it is a complex emergent property of information processing systems, that the hard problem will dissolve once neuroscience and cognitive science advance far enough. This is a coherent position, and it might be right, but it requires a kind of faith, a faith that the explanatory gap between objective physical description and subjective experience is bridgeable in principle, even if it has not been bridged in practice. Others have argued for a more radical position, one that is gaining traction in some unexpected quarters of the scientific and philosophical world. This position, called panpsychism, holds that consciousness, or something like it, some proto-experiential quality, some elementary form of the capacity for experience, is not something that emerges from complex physical processes, but is instead a fundamental feature of reality, present at every level, in every particle, in every quantum field, not necessarily in the rich, self-aware form that you experience it, but in some minimal, primitive form that is the raw material from which complex experience is constructed. Panpsychism is an ancient idea, but it has recently been reformulated in philosophically precise and scientifically serious ways by thinkers like Chalmers, Philip Goff, and Galen Strawson. The argument is not that rocks are conscious in the way you are conscious, but that the experiential properties of complex systems like brains are built up from elementary experiential properties of their constituents, in the same way that the physical properties of complex systems are built up from the physical properties of their constituents. If panpsychism is correct, it means that the standard picture of reality, the picture in which consciousness is a late arrival, a special product of highly complex biological systems, is wrong. Consciousness would be built into the fabric of reality from the beginning, as fundamental as mass or charge, as irreducible as the quantum of action. Reality would not be fundamentally physical with consciousness as an add-on. It would be fundamentally experiential, with the physical world as we know it representing the external structural aspect of something that has an inner experiential aspect at every level. And there is a version of this idea that is even more radical, and that connects back to some of the foundational puzzles in quantum mechanics in a way that is impossible to dismiss easily. The physicist John Archibald Wheeler, one of the 20th century's great physicists and one of its most imaginative, spent the later years of his career developing and advocating for an idea he called it from bit. The idea is that information, not matter or energy, is the most fundamental constituent of reality, that every particle, every field, every quantum of action, every piece of the physical world derives its existence, its itness, from binary choices, from yes-no questions, from bits of information, that the universe is, at its deepest level, an information-theoretic structure. Wheeler was deeply influenced by the measurement problem in quantum mechanics and specifically by the delayed choice experiment. a variation of the double-slit experiment in which the experimental setup that determines whether you are looking for wave behavior or particle behavior is chosen after the particle has already begun its journey. The results are strange almost beyond comprehension. The particle seems to retroactively adjust its past behavior depending on what you choose to measure in its future. Wheeler used this and related experiments to argue that the universe is participatory, that the act of observation, the extracting of information, the asking of yes-no questions by observers, is not incidental to reality, but constitutive of it, that the universe does not have a definite character independent of the observations that are made within it, that in some profound sense the observers create the reality they observe. Wheeler's participatory universe is not the same as the naive idea that you create reality with your thoughts. It is a more precise and more carefully grounded idea, rooted in the formalism of quantum mechanics and in the deep connections between physics and information theory that have been developed over the past several decades. But it points in the same direction that several other lines of inquiry are pointing, toward the possibility that reality is not a self-subsisting, observer-independent structure that would exist in exactly the same form, whether or not any mind ever looked at it. It points toward the possibility that the relationship between mind and world is more intimate, more bidirectional, more constitutive than the standard scientific picture allows, that the universe and the observers within it are not two separate things, with the universe as the grand stage and the observers as incidental members of the audience, but that they are somehow co-arising, co-constituting, that the universe needs observers in some deep sense, that the equations are beginning to hint at, but that no theory has yet fully articulated. This is not mysticism. It is a direction that serious physics is pointing, and it is deeply, fundamentally disturbing, because if it is true, then the picture of reality that science has been building, the picture of a vast, impersonal physical universe that existed for billions of years before any conscious being came along, and that will continue to exist for billions of years after the last conscious being is gone, a universe that does not know or care about the minds within it, might be not just incomplete but in some crucial sense wrong. Let us slow down here, because it would be easy to get carried away, to let the philosophical vertigo of these ideas pull you further than the evidence warrants to start making claims that the science does not support. The ideas you have been encountering, the measurement problem, entanglement, the Hubble tension, the fine-tuning of constants, the hard problem of consciousness, Wheeler's participatory universe, the holographic principle, are all real, all genuinely discussed and debated by serious scientists and philosophers, and none of them have been exaggerated or distorted in this telling, but it would be wrong to present them as a coherent argument for any single conclusion. They do not all point in the same direction in a way that adds up to a clear answer. What they share is not a conclusion, but a quality, the quality of pointing at something that is missing, something that the current framework cannot accommodate, something that sits just outside the edge of what can currently be described or understood. They are symptoms, not a diagnosis, and the disease they are pointing at, if that is the right metaphor, is not any specific physical phenomenon, but something more structural, something about the relationship between the models we build and the reality we are trying to model, something about whether the gap between the map and the territory is a gap that can never be fully closed. There is a concept in philosophy of science called underdetermination, and it is relevant here in a way that is easy to overlook. Underdetermination refers to the fact that for any finite set of observational data, there are in principle infinitely many theories that are consistent with that data. The data does not uniquely determine the theory. The observations you have made do not point to a single correct description of reality. They are consistent with multiple, mutually incompatible descriptions, and there is no purely empirical way to choose between them. You have seen this concretely in the case of quantum mechanics, where the Copenhagen interpretation, the many worlds interpretation, the de Broglie-Bohm pilot, wave theory, the relational interpretation, and a dozen other interpretations all make exactly the same empirical predictions and yet describe completely different underlying realities. This is not a temporary situation that will be resolved when more experiments are done. The interpretations are designed to agree on all predictions. The disagreement is about what is actually happening, about the nature of the underlying reality, and no experiment can answer that question because any answer to it must go beyond what the data can determine. The data is consistent with a universe in which the wave function is real and branches at every measurement event. It is equally consistent with a universe in which there is no wave function between measurements, only a mathematical tool for calculating probabilities. It is consistent with a universe in which there are hidden variables guiding particles along definite paths. All of these are possible. All are consistent with everything that has ever been observed. The universe, as seen through the lens of quantum mechanics, is radically underdetermined, and this underdetermination is not a problem that more data will solve. It is a structural feature of the relationship between observation and reality. The physicist Carlo Rovelli has developed an interpretation of quantum mechanics called relational quantum mechanics that takes this underdetermination seriously and builds a picture of reality from it that is deeply strange, but internally consistent. In Rovelli's view, there is no absolute, observer-independent state of any physical system. The quantum state of a system is always defined relative to another system, to an observer or a measuring device or any physical entity that interacts with it. When two systems interact, each acquires a definite value relative to the other. But there is no fact about what value a system has in absolute terms, independent of any relational context. The wave function does not describe an objective property of the system. It describes the relationship between the system and something else. Reality, on this view, is not made of things with intrinsic properties. It is made of relations, of interactions, of correlations between systems. There are no self-subsisting, property-having entities. There are only networks of relations, patterns of interaction, webs of correlation that temporarily cohere into what we call particles and fields and objects and selves. This is not just an interpretation of quantum mechanics. It is a radical ontology, a complete reconception of what it means for something to be real, and it connects in deep ways to other areas of physics and philosophy where similar ideas are emerging, from the relational accounts of spacetime in general relativity, where the geometry of space is not fixed in advance but is determined by the matter and energy within it, to the process philosophy of Alfred North Whitehead, who argued a century ago that reality is fundamentally constituted not by things but by events and relations. The picture of reality that is beginning to emerge from these converging directions is not the picture of a collection of solid, definite objects existing in a fixed spatial container and evolving through a fixed temporal sequence. It is a picture of a dynamic, relational, fundamentally process-like reality in which things are less fundamental than interactions, in which properties are less fundamental than relations, in which the hard edges of objects dissolve on close inspection into networks of mutual dependence. And then there is time. If space is already unsettling, time is worse, because time is the axis on which your entire inner life runs. Your sense of being you, of being a continuous self with a past and a future and a present, is fundamentally temporal. Your plans, your memories, your anticipations, your regrets, all of them exist only because you are a creature that lives in time. And physics has been quietly undermining your intuitive understanding of time for over a century, without ever quite saying so plainly. You probably know that Einstein showed that time is not absolute, that it flows at different rates for observers in different states of motion, or in different gravitational fields. This is not a theoretical abstraction. It has been measured. The GPS satellites in orbit around the Earth are moving faster than clocks on the surface, and are also in a weaker gravitational field. And both effects change the rate at which their clocks tick relative to ground-based clocks. The discrepancy is small but significant, and the GPS system must correct for it constantly, or the position calculations would drift by kilometers per day. Time dilation is not a philosophical position. It is an engineering fact. But even this is only the beginning of what physics says about time, and the rest of it is considerably more disturbing. General relativity describes space-time as a four-dimensional, geometric structure, a manifold in which the three dimensions of space and the one dimension of time are unified into a single entity. In this description, time is not a flow, it is a direction. The future and the past exist just as much as the present does, laid out in the four-dimensional block of spacetime, with no special status assigned to now, no objective distinction between what has happened, what is happening, and what will happen. The sensation you have of time flowing, of moving from moment to moment of the present being in some sense more real than the past or the future, is not reflected anywhere in the equations of general relativity. The theory is time-symmetric. It makes no distinction between past and future in any fundamental sense. If you took a solution to Einstein's equations describing a particular space-time geometry and ran time backward, you would get another valid solution. The past and the future are, in the equations, interchangeable directions. And this is profoundly at odds with your experience because you experience time as having a direction, as flowing from past to future, as being asymmetric in a way that is so obvious and so pervasive and so total that it seems impossible that the equations could be missing it, but they are missing it, or rather, it is not in the equations at all. The arrow of time, the sense in which time runs in one direction and not the other, is not built into the fundamental laws of physics. It appears to emerge from initial conditions, from the fact that the universe started in an extraordinarily low entropy state and has been moving toward higher entropy states ever since. But why the universe started in such a low entropy state is itself one of the great unsolved problems in physics, a problem that circles back to cosmology and to the fine-tuning questions and to the whole nest of interconnected puzzles that have been accumulating throughout this exploration. The physicist Julian Barber has taken the timelessness of the fundamental equations of physics and run with it in a direction that is both philosophically dizzying and scientifically serious. In Barber's view, time does not exist. Not just that time is relative or that it flows differently in different reference frames, but that time, as a dimension in which things change and evolve, simply does not exist at the fundamental level. The fundamental reality is a vast collection of static configurations of the universe, each one a different arrangement of all the matter and geometry in existence, each one a kind of frozen snapshot, and none of them succeeding each other in any temporal sense. There is no before and after, there is no motion, there is no change. There are only these configurations existing in a timeless space of possibilities that Barber calls Platonia. The experience you have of time passing, of one moment following another, of the present emerging from the past and moving into the future, is an illusion generated by the existence of time capsules, configurations that contain memories and records of other configurations, giving rise to the appearance of a past that was once present and a future that is yet to come. This is not madness. It is a serious attempt to take the timelessness of the fundamental equations seriously and build a picture of reality consistent with them. And the fact that it sounds completely at odds with everything you have ever experienced is not evidence against it. The universe has no obligation to match your experience of it. If Barber is right, or if the block universe picture of general relativity is right, or if the relational interpretation of quantum mechanics is right, or if the many worlds interpretation is right, or if the holographic principle is right, or if the mathematical universe hypothesis is right, then the world you experience, the solid, continuous, three-dimensional, temporally flowing, causally ordered world of objects and events and selves is not the fundamental reality. It is an appearance, an emergent structure, a pattern in something deeper that bears little resemblance to the world as it appears, and the something deeper has not been agreed upon. The physicists and philosophers who have been trying to find it have found different things, or different aspects of the same thing, or perhaps just different ways of describing the same profound mystery. But what they have all agreed on, what all of these different attempts share, is that the common sense picture of reality is wrong. Not wrong in detail, not wrong about the boiling point of water or the orbital period of Mars, but wrong at the level of what reality fundamentally is. Wrong about the nature of space and time and matter and causality and observation and mind, the most fundamental things you believe about the world, the things so basic that you have never had occasion to question them, the things that feel not like beliefs but like direct perceptions of reality. Those are the things that the deepest inquiries in physics and philosophy are calling into question, and the questioning is not over. It is, in some sense, just beginning. There have been moments throughout the history of science when the ordinary understanding of reality underwent a fundamental shift, and the people who lived through those moments often did not fully appreciate what was happening. When Copernicus proposed that the Earth moved around the Sun, the first response was not enlightenment but resistance, because the proposal violated something that felt not like a theory, but like direct experience. You can feel the Earth standing still beneath you. You can watch the sun move across the sky. To say that this experience is misleading, that the Earth is in fact hurtling through space at enormous speed, required not just a new theory, but a new relationship between experience and reality, a new willingness to say that what things appear to be and what they are can be radically different. When Newton showed that the force pulling you toward the Earth was the same force holding the Moon in its orbit, it required a conceptual leap that was not just mathematical but ontological, a recognition that the intuitive division of the world into the earthly and the celestial was an artifact of limited perspective, not a feature of nature. When Darwin showed that the diversity of life arose not from special creation, but from variation and selection over vast time, it required not just accepting a new theory, but dismantling an entire framework for understanding what life is and where it comes from. In each case, the resistance came from the same place, from the deep human need to live in a world that makes sense, that matches experience, that reflects back to the mind a picture it can inhabit. The new ideas were threatening, not because they were implausible or poorly argued, but because they were disorienting. They required you to live in a world that was not what it appeared to be. What is happening now feels like something similar, but at a deeper level. The previous revolutions changed the content of the scientific picture of reality, replacing one description with a better one, but they left the framework intact. They still described a world of objects moving through space and time, a world of causes and effects, a world that existed independently of any observer, a world that operated by consistent laws that could be discovered through careful observation and mathematical reasoning. The current situation is different because what is being challenged is not the content of the picture, but the framework itself, the very categories that all previous descriptions used, the ideas of space, time, causality, matter, observation, and self. When these categories are in question, it is not clear what a replacement would even look like, because every replacement that has been proposed still uses some of these categories and, therefore, still inherits the problems that come with them. The search for a unified theory of quantum gravity is not just a search for a better equation. It is a search for new conceptual categories, new ways of organizing experience and thought that do not yet exist. And there is a real possibility, acknowledged by many of the physicists working on these problems, that the conceptual tools needed to describe reality at the deepest level have not yet been invented, and that inventing them will require a kind of intellectual effort that is qualitatively different from anything science has done before. Let yourself sit with that for a moment, because it is genuinely extraordinary. The enterprise of science, the most powerful knowledge-generating enterprise in human history, is facing a situation in which the next step forward may require not just new data or new theories or new mathematics, but new concepts, not refinements of existing concepts, but genuinely new ones, with no predecessors, built from scratch, emerging from a creative intellectual act that has not yet happened. The history of such moments is actually quite short. The invention of the calculus by Newton and Leibniz was such a moment. The development of non-Euclidean geometry by Riemann was such a moment. The creation of quantum mechanics was such a moment. Each of these involved the construction of a conceptual framework that did not previously exist, that could not have been anticipated from within. The existing framework that arose from a combination of mathematical exploration and deep attention to the anomalies that the existing framework could not accommodate. And each of them changed not just what science knew, but what it was possible to know, opening up entire domains of reality that had been invisible to the previous conceptual vocabulary. The next such moment may be close, or it may be decades away, or it may require the kind of mind that has not yet been born. But it is clear, from the accumulating weight of the anomalies and the depth of the contradictions, that it is needed, that the current framework is not just incomplete at the edges, but broken at the center. One of the strangest and most persistent features of the situation is the way in which the deepest problems in physics keep circling back to the same cluster of ideas, coming at them from different directions, wearing different mathematical disguises, but pointing at the same underlying mystery: the measurement problem in quantum mechanics and the hard problem of consciousness. Both point at the relationship between physical processes and subjective experience, the fine-tuning of the constants of nature and the string theory landscape. Both point at the question of why the universe has the character it has rather than some other character, why these laws rather than different ones, why this universe rather than another, the incompatibility of quantum mechanics and general relativity and the holographic principle both point at the question of what space and time are at the most fundamental level, whether they are real in the ordinary sense or emergent or illusory. The underdetermination of theory by data and the Gödelian incompleteness of formal systems both point at the limits of knowledge, at the possibility that there are truths about reality that cannot be reached by the methods of science. These are not separate problems. They are facets of the same problem. They are the same question asked in different languages, and the question at its core is this: what is real, and how can we know? This question is ancient. Philosophers have been asking it since before Plato, but what is new is the context in which it is now being asked. It is no longer being asked in the abstract as a purely philosophical exercise, disconnected from empirical inquiry. It is being forced on science by the anomalies and contradictions in the most successful theories ever built. The question is no longer optional. It can no longer be deferred to philosophers while physicists get on with the calculations. The calculations themselves are demanding an answer. The equations are reaching a point where they cannot be extended without a deeper understanding of what they are equations of. The theories are reaching a point where their internal contradictions can no longer be papered over with clever approximations and regime-specific idealizations. The data is reaching a point where it is demanding explanations that the existing framework simply does not have. The question of what is real is no longer a question that science can afford to leave unanswered, because the answer, or the lack of it, is sitting in the way of every attempt to go further. And here is perhaps the most disorienting aspect of all of it, the piece that is hardest to hold without vertigo. You are not an outside observer of this situation. You are inside it. You are not a detached mind contemplating a puzzle. From a safe distance, you are part of the puzzle. You are a physical system, built from quantum mechanical particles that do not have definite properties until measured, held together by forces that emerge from quantum fields, embedded in a space-time that is curved by the mass of your body, a space-time that may itself be emergent from something more fundamental. You are a biological system, shaped by 4 billion years of evolution on a particular planet around a particular star in a particular galaxy in a particular region of the universe. Your brain built by selection pressures that had nothing to do with understanding quantum gravity or cosmological fine-tuning, and everything to do with surviving long enough to reproduce. You are a conscious system, generating experience in a way that no physical theory can currently explain, constructing a model of reality that is your only access to reality, living inside a representation and calling it the world. You are a temporal system, experiencing yourself as moving through time even though the fundamental equations of physics do not distinguish past from future. You are a relational system, defined by your interactions with other systems, your identity constituted by connections and context rather than by any intrinsic essence. You are, in short, exactly the kind of thing that the deepest questions in physics and philosophy are about. The mystery is not out there, in distant galaxies or subatomic particles. It is in here, in the very experience of being, in the fact that there is something it is like to be you, reading these words, in this moment, in this universe. The philosopher Thomas Nagel wrote a famous paper called "What Is It Like to Be a Bat?", in which he argued that no amount of objective, third-person scientific information about the sonar system of bats would ever give you access to the subjective, first-person experience of being a bat, of perceiving the world through echolocation from the inside. The eye, subjective perspective, the what it is like, is something that objective descriptions leave out by their nature, because objective descriptions are specifically designed to be perspective independent, to capture what is the case regardless of who is looking. And this is exactly what science does, and does brilliantly. But it means that science, by design, leaves out the one thing that is most immediately and undeniably present to you, your experience. Science describes the world from the outside, and you live in the world from the inside. And the gap between those two perspectives is not bridgeable by any amount of additional scientific information, because additional scientific information is more of the same kind of thing, more objective description. And what is needed is an account of the relationship between objective description and subjective experience. And that account does not yet exist. What makes this more than an abstract philosophical puzzle, what gives it urgency and weight and a kind of personal pressure, is that the question of consciousness is not separable from the question of observation in quantum mechanics. The measurement problem, at its heart, is about what happens when a quantum system interacts with a measuring device. But when you try to describe the measuring device quantum mechanically, it becomes a quantum system too, and the problem just shifts upward. You need a description of the interaction between the measuring device and the environment, but the environment is also a quantum system. You can keep going up this chain, including more and more of the world in the quantum description, and the wave function just keeps growing, incorporating everything in superposition, never resolving into a definite outcome. The only place the chain ever seems to stop, the only place where definite outcomes seem to be registered, is in conscious experience, not in the detector, not in the amplifier, not in the computer that records the data, but in the mind of the scientist reading the printout. This observation, uncomfortable and philosophically fraught as it is, lies at the heart of certain interpretations of quantum mechanics that take consciousness seriously as a physical variable. The physicist Eugene Wigner proposed in the 1960s that consciousness causes wave function collapse, that it is the interaction with a conscious observer that transforms the indefinite quantum superposition into a definite classical outcome. This view has been out of fashion for most of the intervening decades, dismissed as giving an unjustified special status to mind in a universe that seems to operate perfectly well without any such privileging. But it has never been ruled out, and the fact that it cannot be ruled out, that the measurement problem remains genuinely unsolved after a century, means that the possibility that consciousness plays a fundamental role in the physics of the universe cannot be closed off. Some researchers have tried to make this idea precise and empirically testable. The physicist Roger Penrose and the anesthesiologist Stuart Hameroff have proposed a theory of consciousness called orchestrated objective reduction, or ORCH-OR, in which consciousness arises from quantum processes in microtubules, protein structures inside neurons, and in which the collapse of quantum superpositions in these microtubules is a genuine physical event with specific quantum gravitational implications. The theory is controversial, and most neuroscientists and physicists are skeptical of it, but it is notable for attempting to bring together quantum mechanics, the physics of gravity, and the biology of the brain into a single framework for understanding consciousness. It is, regardless of whether it is correct, an example of how seriously some researchers take the possibility that consciousness is not peripheral to physics, but central to it. And even if ORCH-OR is wrong in its specific details, the broader intuition it embodies, that the relationship between mind and matter cannot be understood by treating mind as a passive byproduct of matter, that any complete theory of physical reality must have something to say about why that reality is experienced from the inside, is one that is becoming harder and harder to dismiss. There is something almost vertiginous about the realization that all of these lines of inquiry, the quantum measurement problem, the hard problem of consciousness, the fine-tuning of the constants, the holographic principle, the simulation hypothesis, the Gödelian incompleteness of formal systems, and the failure of physicists to unify quantum mechanics and gravity, converge on the same set of questions about the nature of observation, information, and the relationship between the observer and the observed. It is as though reality, examined carefully enough from enough different directions, always leads back to the same central mystery, not the mystery of what things are made of. That question has been answered provisionally at successively deeper levels and may continue to be answered. But the mystery of why there are things at all, why there is experience, why the universe is comprehensible in the first place, why the mathematics works, why any of this is rather than nothing, that mystery does not diminish with inquiry. It deepens. Every answer generates a deeper question. Every theory opens up new spaces of ignorance. Every advance in understanding reveals more clearly the shape of what is not understood. And the shape of what is not understood keeps looking less like an ordinary gap in knowledge and more like a structural feature of the situation, a permanent, irreducible incompleteness that is not a failure of science but a fact about reality. You might feel at this point a particular kind of cognitive discomfort, a sense that the ground is not quite where you left it, that the comfortable solidity of ordinary experience is subtly different than it was before you began this inquiry. This is not an accident, and it is not a failure of reasoning. It is the appropriate response to taking the question seriously. The great physicist Richard Feynman once said that if you think you understand quantum mechanics, you don't understand quantum mechanics. He said this not as an admission of defeat, but as a recognition that the theory demands a kind of intellectual honesty about the limits of understanding that ordinary, scientific confidence tends to paper over. The same honesty is demanded by all of the questions that have been raised here, not the honesty of ignorance, of simply not knowing something that could in principle be known, but the honesty of depth, the recognition that the questions are real, that they do not have easy answers, that they point at something fundamental about the relationship between mind and world, and that sitting with them, really sitting with them, without reaching for a premature resolution, is itself a form of understanding. The physicist and philosopher David Deutsch has argued that the ability to generate increasingly good explanations of reality is the fundamental capacity that distinguishes humans from all other known entities, and that this capacity is in principle unlimited, that there is no question that cannot in principle be answered by an explanation of sufficient depth and creativity. Deutsch is an optimist about the reach of human knowledge, and his optimism is grounded in a sophisticated philosophical position about the nature of explanation and the openness of the universe to inquiry. But even Deutsch acknowledges that the current situation in physics is unprecedented, that the failure to unify quantum mechanics and general relativity represents a failure not just of particular theories, but of the explanatory strategies that have worked in every previous case. He believes the solution will come, but he cannot say when or what form it will take, or whether it will require conceptual innovations as radical as those that gave birth to quantum mechanics. And that uncertainty is itself significant. The most optimistic, serious thinker in the field cannot say when the impasse will be broken, or how. That should tell you something about the depth of the impasse. There is a metaphor that has been used by several physicists to describe the current situation, and it is worth dwelling on because it captures something important about the quality of the mystery. The metaphor is of a jigsaw puzzle. When you are working on a jigsaw puzzle, you have pieces and you have the image on the box, and you know that the pieces fit together to form a coherent picture. The challenge is to figure out where each piece goes. But what if you were working on a jigsaw puzzle without the image on the box? What if you did not know what the completed picture looked like? You could still fit pieces together, find local regions of consistency, discover that certain pieces clearly belong next to each other, but you would have no guarantee that the local regions you were building were actually part of the same picture. No way to know whether the piece you were holding belonged to the puzzle you were working on or to a different one entirely. And what if, in addition to not having the picture on the box, you were not sure the puzzle was complete, not sure all the pieces were present, not sure that what you had was a puzzle at all, rather than a collection of pieces from different puzzles that happened to be mixed together? This is closer to the situation in fundamental physics right now. The pieces are extraordinary. The equations work brilliantly in their respective domains, but there is no picture on the box. There is no agreed-upon idea of what the completed theory would look like, no consensus on what questions it would answer, no shared vision of what reality looks like at the level where all the pieces fit together. And in the absence of that vision, the work of fitting pieces continues, but without the sense of direction that knowing the destination provides. Some physicists have proposed that the picture on the box might be something deeply unfamiliar, something so different from the ordinary image of reality that recognizing it when you see it would require a kind of conceptual revolution that is hard to prepare for. The theoretical physicist Nima Arkani Hamed, one of the leading figures in contemporary high-energy physics, has argued that both space and time are approximate emergent concepts that will not appear in the final theory, that the fundamental description of reality will be something entirely different, a kind of timeless, spaceless mathematical object, from which the appearance of space-time will emerge as a large-scale approximation, the way the smoothness of water emerges from the jostling of individual molecules. He and his collaborators have been developing mathematical structures called amplituhedra and associahedra, geometric objects that encode the probabilities of particle interactions without any reference to space, time, or locality. Objects that seem to contain all the physics but none of the ordinary physical concepts. These structures are beautiful and suggest that there is a deeper level of mathematical reality beneath the space-time description, a level where the architecture is simpler and more elegant and perhaps more transparent, but also one that has no resemblance to the world of tables and chairs and sunsets. The connection between the world of the amplituhedron and the world of your experience is not something that anyone has yet been able to make explicit. It is an open question whether anyone ever will. And this brings you back in a circling way to where you started, to the world as it appears to you, the world of solid surfaces and reliable cause and effect and consistent physical laws and the continuous flow of time. This world has not changed. It remains what it has always been, extraordinarily reliable, extraordinarily consistent, extraordinarily well described by science at the scales that matter for ordinary life. The floor is still under your feet. The coffee is still cooling. The sun will still rise tomorrow. All of the anomalies and contradictions and deep puzzles that have been explored here operate at scales and in regimes that have no direct impact on your everyday experience. The quantum weird. Think about what it means to live in a universe where a quarter of all the matter is invisible and has never been directly detected, where the energy driving the accelerating expansion of space is completely unexplained by any theory, where the most fundamental constituents of matter do not have definite properties until they are observed, where two particles can be connected across arbitrary distances in ways that violate every classical notion of how information and influence can travel, where the two most successful theories in physics are mutually inconsistent, where the arrow of time, the most pervasive feature of your experience, has no explanation in the fundamental equations, where the constants of nature are tuned to extraordinary precision in ways that permit the existence of stars and planets and life, and no one knows why, where the act of observation seems to play a role in constituting what is observed, where consciousness, the most immediate and undeniable fact of your existence, finds no place in any physical theory, where the leading candidate for a final theory of everything predicts 10 to the 500 possible universes and cannot tell you which one you are in, where the most powerful formal systems in mathematics contain true statements that can never be proved, where the experience of a continuous, stable, three-dimensional world persisting through time might be, in some sense, not yet fully articulated, a construction rather than a perception, a model rather than a direct acquaintance with reality. This is the universe you live in. This is what the most careful and rigorous inquiry into the nature of things has revealed. Not a comfortable, fully understood, mostly solved picture with a few details outstanding. A picture that is, at its most fundamental levels, deeply, structurally, disturbingly incomplete. And the incompleteness is not random. It is patterned. The same themes recur in every direction you look. The theme of observation, the recurring suggestion that what is real cannot be fully separated from what is observed, that the boundary between the measuring mind and the measured world is not as clear as it seemed. The theme of emergence, the recurring suggestion that the familiar categories of reality, space, time, particles, forces, even consciousness, are not fundamental but derived, not the bedrock, but the surface, built up from something deeper that does not resemble them. The theme of information, the recurring suggestion that information, not matter or energy, is the most fundamental currency of reality, that what the universe is made of is not stuff but structure, not substance but relationship. The theme of incompleteness, the recurring suggestion that reality exceeds every description of it, that the map always falls short of the territory, that there is always more truth than any framework can contain. These themes are showing up in quantum mechanics and in cosmology and in mathematics and in the philosophy of mind and in the foundations of physics, showing up independently, arriving from different directions, wearing different technical clothes, but pointing at the same thing. Something about reality is different from what the framework assumes. Something about the relationship between mind and world, between description and reality, between the model and what it models, is not what science has been implicitly assuming it to be. The cracks are not random damage, they are a pattern. And patterns, when they appear in different places, in different contexts, in different disciplines, have a habit of meaning something. You have been living inside a story about reality. Everyone has. The story was built over centuries by some of the greatest minds in history, tested against experience at every step, refined and extended and deepened until it became the most reliable and productive framework for understanding the world that has ever existed. The story says that reality is made of matter and energy, governed by fixed laws playing out in space and time, available to understanding through careful observation and mathematical reasoning, fundamentally separate from the minds that observe it. This story has given humanity medicine and technology, and the ability to send machines to the edges of the solar system and to image the shadows of black holes a billion light years away. It is an extraordinary story. It is, in most respects, the best story humanity has ever told, but it is a story. And like every story, it has been built on assumptions, some of them explicit and some of them so deep that they have never been fully examined. Assumptions about what counts as real, about what counts as an explanation, about what the relationship between the mathematical description and the physical world actually is, about whether the observer can ever be fully separated from the observed, about whether the human mind is an adequate instrument for grasping the deepest truths of nature. And now those assumptions are being tested, not by philosophers sitting in armchairs, but by physicists running experiments, and by mathematicians developing new structures, and by neuroscientists probing the inner architecture of experience. And the testing is revealing something uncomfortable. The assumptions do not all hold. The story has limits. The frame is too small for everything that needs to fit inside it. What comes next is not known. And this is not a rhetorical device or a dramatic pause before a reassuring conclusion. It is literally true. The physicists and mathematicians and philosophers who are working on these problems do not know what comes next. They do not know whether the solution to the measurement problem will require a modification of quantum mechanics or a new understanding of what observation means, or a radical reconception of the relationship between mathematics and reality. They do not know whether the resolution of the Hubble tension will require new physics in the dark sector or a modification of the cosmological model or something no one has thought of yet. They do not know whether the unification of quantum mechanics and general relativity will come from string theory or loop quantum gravity or some entirely new framework. They do not know whether consciousness is an emergent property of complex information processing or a fundamental feature of reality or something that requires categories that do not yet exist. They do not know whether space and time are fundamental or emergent. They do not know whether the universe is the only universe or one of an enormous multiplicity. They do not know whether the constants of nature are explained by some deep principle or selected anthropically, or simply are what they are without any explanation. All of these questions are open. All of them are being actively worked on. None of them have answers. This is not a temporary situation. It has been this way for decades on some of these questions, and the passage of time and the accumulation of effort have not closed them. They have, in some cases, deepened them. And yet there is something in this situation that is not only unsettling, but also, if you can hold it at the right angle, extraordinary. You are living at a moment in history when the framework that humanity has used to understand reality is showing its limits, when the questions that lie beyond those limits are clearly visible, even if the answers are not, when the shape of the next great conceptual revolution is beginning to emerge from the pattern of the anomalies, when the enterprise of understanding the universe is at one of those rare and vertiginous threshold moments when everything known points toward something not yet known, and the tension between the two is almost unbearable. These moments do not come often. There have been perhaps 3 or 4 of them in the history of science, moments when the existing picture was clearly inadequate and the new picture was clearly needed but had not yet arrived, moments of productive crisis when the pressure of unresolved questions was building toward a breakthrough. The Newtonian synthesis was preceded by such a moment. Quantum mechanics was preceded by such a moment. General relativity was preceded by such a moment. And now, by every indication that careful observers of science can find, something similar is building. Not imminently, perhaps, and not with any guarantee of resolution, but building. The questions are too deep and too well defined and too clearly anomalous to remain unanswered forever. The universe has always, eventually, yielded its secrets to sustained and rigorous inquiry. There is no particular reason to think this time will be different, but there is also no particular reason to think the secrets that are yielded will be the kind that make you comfortable. The history of science suggests the opposite. The history of science suggests that every deeper layer of reality is stranger than the one above it, and the layer that is currently beckoning, the layer that lies beneath space and time and quantum mechanics and consciousness, the layer that all of these anomalies are pointing at, is likely to be stranger than anything the history of science has prepared you for. There is a line from the physicist J.B.S. Haldane that has been quoted many times, but that never quite loses its force. He wrote that the universe is not only queerer than we suppose, but queerer than we can suppose. He meant this as an expression of intellectual humility, as a reminder that the human imagination, however fertile and however disciplined, is still a product of evolution, still shaped by the particular environment in which it developed, still bounded by the cognitive architecture that was built for navigating a very specific kind of world at a very specific range of scales, the universe, which was not built for human comprehension, which did not take any account of what human minds can grasp when it arranged its quarks and its dark energy, and its space-time geometry and its quantum fields, has no obligation to be comprehensible. It has no obligation to be beautiful, though it often is. It has no obligation to yield to inquiry, though so far it has. It has no obligation to be the kind of thing that a primate brain, however enlarged and however assisted by mathematics and experiment, can fully grasp. And the deepest questions in current physics are precisely the ones where this limit might be closest, where the universe might be calling on conceptual resources that the human mind simply does not have. This is not pessimism. It is realism about the relationship between minds and the reality they are trying to understand. The astronomer and writer Carl Sagan once said that we are a way for the cosmos to know itself, that the atoms in our bodies were forged in stars, and that consciousness is, in some sense, the universe looking at itself through particular configurations of matter. It is a beautiful thought, and it captures something true about the extraordinary fact that the universe has produced beings capable of asking questions about it. But there is a haunting underside to it that Sagan's phrasing does not quite surface. If we are a way for the cosmos to know itself, we are also a very particular and limited way. We see in a narrow band of the electromagnetic spectrum. We hear in a narrow band of frequencies. We live on the surface of a single planet around a single star in a single galaxy among 2 trillion galaxies. We evolved over a few million years in conditions that are, cosmically speaking, extraordinarily specific and atypical. The sample of reality from which we have built our understanding is vanishingly small. The tools we use, our senses, our mathematics, our instruments, are extraordinary by the standards of the biological world, but are they adequate for the task of understanding a universe that may operate on principles for which our cognitive architecture has no analogs? That question is not answerable from inside the situation. You cannot step outside your own cognitive architecture to check whether it is adequate. You cannot compare your understanding of reality with reality itself to see how much has been left out. You are inside the picture, and the picture is all you have. And so you are left with something that is difficult to name precisely, but that is unmistakable in its quality. It is not quite uncertainty, because uncertainty implies a specific question whose answer you do not yet have. It is not quite ignorance, because ignorance implies the absence of knowledge, where knowledge could in principle be present. It is something more like a structural condition, a feature of the situation that goes beyond the absence of particular answers. It is the recognition that the world you live in, the world that feels so solid and so reliable and so fully present to you, is related to the underlying reality in a way that is not fully transparent, that is mediated by the architecture of your perception and the limitations of your cognition and the particular accidents of evolutionary history that produced a mind of this type in a universe of this type at this particular moment. The relationship between the world as it appears and the world as it is has always been obscure, has always been the deepest question in philosophy, has always resisted final resolution. But what is new is that science itself, the enterprise that seemed to have made steady progress toward closing that gap, is now revealing that the gap may be not just larger than it seemed, but differently shaped. Not the gap between what is known and what could be known, but the gap between what can be modeled and what is real, between the description and the described, between the experience of understanding and actual understanding. The world looks the same as it did before you began this inquiry. The room around you has not changed. The laws of physics are still operating exactly as they were. The sun is still the same distance away. The atoms in your body are still doing what they were doing. Nothing has shifted in the external world. But something has shifted, or something should have shifted, in the way you are relating to it, in the confidence with which you are placing your feet on the floor of the known and assuming it will hold. Not because the floor is about to give way. It is not. Not because the laws of physics are about to change. They are not. But because the floor you are standing on is not the deepest level there is, and the deepest level is not the floor you thought it was, and what is down there beneath the reliable surface of ordinary experience, beneath the equations of quantum mechanics and general relativity, beneath the Standard Model and the Lambda CDM cosmology, beneath the mathematics and the experiments and the theories, is something that no one has yet seen clearly, and that something, whatever it is the actual structure of the world, the actual nature of reality, and it is not what you were told, and no one yet knows what it is. Perhaps the most honest thing that can be said at the end of all of this is not a conclusion. Conclusions are for situations where the inquiry has reached a natural stopping point, where the evidence has converged on an answer, where the tension between the question and the unknown has been resolved. None of that is true here. The inquiry has not reached a stopping point. The evidence has not converged. The tension has not been resolved. If anything, it has intensified. Every decade that passes without a resolution to the measurement problem, or the unification of quantum mechanics and gravity, or the explanation for the cosmological constant, is a decade that makes the problem harder, not easier. A decade that rules out more of the simple solutions and forces the inquiry into deeper and less familiar territory. The space of possible answers is not shrinking. In some ways it is growing, and the questions themselves are changing character, shifting from questions about what the universe contains to questions about what reality is, from questions about the properties of things to questions about the nature of existence, from questions that science knows how to ask to questions at the edge of what can be asked at all. What you are left with then is not an answer, but an orientation that takes seriously the possibility that reality is stranger than any current framework can capture, that the stable, predictable, law-governed universe of classical science is a vast and reliable and enormously useful approximation to something that is neither stable nor predictable nor governed by laws in any sense that would be familiar to the mind that built classical science, that the experience of understanding, the feeling that you have grasped something true about the world, is not the same as actual understanding, is not a guarantee that the model corresponds to the reality, is not a proof that the concepts being used are adequate for what they are trying to describe, that the silence of the dark matter detectors and the tension in the Hubble constant, and the unresolved measurement problem and the incompatibility of the two greatest theories in physics are not technical issues waiting for technical solutions, but signs pointing in a direction that has not yet been fully identified, toward a level of reality that has not yet been reached, that the universe, 14 billion years old, 13 billion light years across, containing 2 trillion galaxies, and an incomprehensible number of stars and planets, and perhaps an incomprehensible number of other universes, vast and old and intricate beyond all imagination, does not owe you, or anyone, a comprehensible face, and yet you are here, conscious, curious, reaching out with the extraordinary instrument of a mind built by 4 billion years of biological evolution, asking questions about the nature of the thing you are embedded in, refusing to accept the surface as the final word, pushing against the limits of the known and the knowable, with the same restless, irreversible drive that brought humanity from fire to quantum computing in the blink of a cosmic eye. Whatever is wrong with reality, whatever the cracks in the foundation mean, whatever lies beneath the reliable surface of the world you know, you are already inside it, you are made of it, you are an expression of it. The quantum fields that refuse to be fully understood are what your atoms are made of. The space-time that curves and bends and may not be fundamental is what your body moves through. The dark matter that has never been detected is presumably flowing through you right now as it flows through everything, invisible and silent and real. The consciousness that no physical theory can explain is the very thing that is reading these words and following this thread and feeling, perhaps, some of that quality of vertigo, that subtle shift in the texture of the world that comes from taking the questions seriously. And the questions will not go away. That is the thing about the deepest questions. They do not resolve themselves into comfortable silence just because you stop thinking about them. They wait, they persist, they emerge again in the middle of the night or at the edges of attention when the noise of ordinary life falls briefly quiet and the strangeness of existence reasserts itself. The strangeness of the fact that anything exists at all, that the universe is the way it is and not some other way, that it is comprehensible enough to have produced beings who can ask whether it is comprehensible, that the mathematics works, that the laws are what they are, that you are here, now, in this moment, experiencing something, alive in a universe whose nature is unknown to you in ways that go all the way down. These are not comfortable questions. They are not the kind of questions that, once asked, let you return unchanged to the ordinary world. They change the texture of everything, subtly, permanently, in a way that cannot be reversed. The ordinary world looks the same, but it sits differently in the mind, the solidity of it a little thinner, the reliability of it a little more provisional, the familiarity of it a little more like a surface than a depth. There is something that has been present throughout all of these explorations, threading through the quantum anomalies and the cosmological tensions and the mathematical incompleteness and the philosophical puzzles, something that is harder to name than any of the specific problems, but that gives the whole inquiry its particular quality of urgency. It is the sense that you are close to something, not close in the sense of about to find an answer, but close in the sense of having come, through all of this careful and sometimes painful inquiry, to a place where the question is finally in clear view, where you can see its shape even if you cannot yet see what it is pointing at, where the contours of the mystery are clear enough that you know you are looking at the right thing, even if you do not yet know what the right thing is. The universe is not arbitrary, or not entirely arbitrary. The anomalies are patterned. The problems are connected. The failures of the framework all point in the same direction, and that direction, vague and unresolved as it remains, is a direction. It is a bearing. It is perhaps the most important bearing that human inquiry has ever taken, toward whatever is underneath space and time, toward whatever is more fundamental than matter and energy, toward whatever the relationship between mind and world actually is, toward whatever the universe is, at the level where the questions finally stop generating deeper questions and something like an answer begins to emerge. Or perhaps not. Perhaps the questions do not stop. Perhaps the universe has no bottom, no final level, no deepest layer where everything makes sense and the architecture is finally visible and the mystery is resolved. Perhaps reality is questions all the way down, an infinite regress of deeper and deeper frameworks, each one incomplete, each one pointing beyond itself, each one revealing a new horizon just as it closes in on what it thought was the destination. This too is a possibility that the current situation does not rule out. Gödel suggests it. The underdetermination of theory by data suggests it. The infinite flexibility of the string landscape suggests it. The unresolvable tension between the objective picture of science and the subjective fact of experience suggests it. Perhaps the universe is not the kind of thing that can be fully known, not because it is hiding something, not because of any failure of intelligence or method, but because knowing requires a knower, and any knower is inside the thing. Being known and being inside something changes what you can know about it in ways that are irreducible and permanent and perhaps productive of the kind of open-ended, horizon-maintaining mystery that makes inquiry possible in the first place. Perhaps the incompleteness is not a bug. Perhaps it is the feature that makes everything else possible. You started here, in this room, in this moment, reading words on a screen, inside a body that is inside a world that is inside a universe that is inside perhaps something larger and stranger and more fundamental that does not yet have a name. You came with the ordinary assumption that reality was, beneath its surface complexity, basically understood, basically stable, basically reliable, basically what it appeared to be. You have traveled through the quantum world, where particles refuse to be definite until looked at, where distant things are instantly connected, where the act of observation changes what is observed. You have traveled through cosmology, where a quarter of the universe is invisible and unexplained, where the expansion rate of space disagrees with itself, where the energy of the vacuum is off by 120 orders of magnitude from what it should be. You have traveled through the foundations of mathematics, where every formal system contains truths it cannot prove. You have traveled through the philosophy of mind, where consciousness, the most immediate fact of your existence, finds no home in any physical theory. You have traveled through the geometry of space-time, where time might not flow and space might not be fundamental, and the 3 dimensions of your experience might be a projection of something 2-dimensional, or 10-dimensional, or no-dimensional at its base. And you have arrived, not at an answer, but at a question, at a very specific, very deep, very unresolved question that sits underneath all of the specific anomalies and all of the specific contradictions and all of the specific failures of the framework. The question is simply this: what is real? Not what are things made of, not how do forces work, not how did the universe begin. Those are versions of the question, important and productive versions, but versions. The deeper question is, what does it mean for something to be real at all? What is the relationship between the mathematical structure and the physical existence, between the description and the described, between the observer and the observed, between the experience and the thing experienced, between the model and the territory, between the inside and the outside, between the mind that asks and the universe that is asked? This question is not new. Philosophers have asked it for thousands of years. But what is new is that physics has now reached the point where it cannot avoid the question, where the internal inconsistencies and the unexplained anomalies and the failures of unification are forcing it to the surface, where the enterprise of describing reality in purely objective, mind-independent mathematical terms has run into limits that the enterprise itself cannot account for. The question of what is real has become a scientific question, not in the sense that it can be answered by an experiment, but in the sense that no experiment can be fully interpreted, no theory can be fully understood, no measurement can be fully trusted without some answer to it. The question is inside the science now. It has always been there, implicit and unexamined, but now it is visible. And visible, unanswered questions in the history of science are how revolutions begin. So here you are, in a universe that works mostly, in a universe that is describable mostly, in a universe that is knowable mostly, in a universe that is reliable mostly. But the mostly is carrying more weight than it used to. The mostly is sitting differently than it did before. The mostly is the sound of the crack running through the foundation, not catastrophically, not visibly, not in a way that changes anything about your immediate experience or your daily life, or the boiling point of water or the orbital period of the Earth around the Sun, but deeply, structurally, at the level where the most fundamental questions are asked and where the most fundamental answers are needed, and where, right now, in the laboratories and offices and seminar rooms and late-night calculation sessions of some of the most brilliant people alive, the answers are not coming. The foundation is holding, but it is not as solid as it was, and the question of what is underneath it, of what would be revealed if you could somehow remove the floor and look at what it is resting on, at what reality looks like beneath the reliable surface, beneath the equations, beneath the mathematics, beneath the measurements, beneath the models, beneath the mind doing the modeling, is still open, still unanswered, still waiting. And the waiting has a particular quality now, a charged, pressurized quality, the quality of a question that has been asked carefully enough and pursued rigorously enough that it is no longer possible to pretend the answer is just around the corner. The answer might not be around any corner you can see from here. It might require a corner that has not yet been built. And between here and there, between the reality you know and the reality that actually is, something remains, unknown, unnamed, unresolved, waiting for a mind that has not yet been born, or a concept that has not yet been thought, or a question that has not yet been asked in quite the right way. And until then, you are here, looking at the world, and the world is looking back, and neither of you fully knows what the other is.